GM! GM! Can you hear me? Let me know in the chats if it sounds okay. Yo, 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 yo. Tricid in the house. We have Aidan Dracic. GM. Rolando, Tricid West again. John Frost. Mad Mike. Oi, oi, oi. Mad Mike is in the house. Jesus. Made of Stardust. Amazing. Okay. Okay, I guess you can hear me. GM, you fucking hash heads. That's how we introduce. That's how we talk to each other now. How's your mining going? How's your mining going? Let me know. How's your machines? Are the machines working? Are those GPUs hashing? Are they guessing? You gotta hash it, man. You gotta hash to get the stash, if you know what I mean. You know? Good. So what should we talk about today, you think? Let me know. Has there happened anything significant? Wow. Okay. So let's get the elephant in the room. Let's get the elephant in the room. X1. Okay. I didn't see that coming. I can tell you that much. That was a pretty baller move. I have to say. It is what it is. You do great stuff. People take it. It's happened in my life many times. I'm not surprised that it happens. I think we will have to, in our journey, get used to people doing so for whatever reason. On the upside, on the plus side, here's a $1 billion organization who just gave us some alpha recognition, which is pretty cool. You know, we're just trailer trash, normal grassroots people. Okay, we're not really trailer trash because we take showers. We're not like Hex, but we listen. It was a shitty move from their end, like 100%. You can't. It's like no doubt. This space should be. This is just my opinion. This space should be about innovation. Okay, so at least be innovative in the name. what the fuck? To get some respect, especially if you're also going to fork. They're using Polygon CDK chain developer kit. But okay, let's understand the situation. I think like fundamentally that there is a difference in values, to be honest. They have a consumer focus and we have a crypto focus. So it's a corporation. We also saw what they did with the gas price. Like, is it really crypto if you can manipulate the gas price like they did? So, you know, it's not the fact though that we are getting attacked or that people are doing something like that to us, because it will happen many times. Oh, Jack's in the house. Git clone invitation. Yeah, exactly. But it's how we respond to it. Okay, so but I guess we'll have to kick their ass now. What do you think? We will never win with being salty though. Okay, it's just like it's not who we are. We're not going to sue them or anything. We don't sue people if they take our code or name. So you know, we win with tech. That's how we beat them. We win with tech and with better community. That's it. So let's focus on that. Oh, Crypto Bra, all the OGs are in the house. So cool to see. Thanks for being here, guys. I love all of you. Yeah, you know, we have a pretty cool crew. We're Senians, we're vampires, we're hash heads, we're fucking hash heads. So it was funny because let's see what we're gonna do about it. Jack just called me before. He has some fucking crazy ideas, to be honest. He woke up 4:30. So was interesting. But let's see. Interesting with Polygon CDK. We abandoned that Polygon some time ago. We could also call it like triple X1 because we saw what it did with adoption. Tell them about the BPS. What's that? BPS. I forgot what it was. We talk so much bullshit. Anyway, guys, let's leave it at that for now, because oh, okay, yeah, I know BPS now. Is it? Okay, I'll tell you about BPS. Short story. I was talking to Jack. He was sitting outside the Starbucks testing the game and getting amazing TPS with the Starbucks Wi-Fi. I'm going to talk about that later. And yeah. And behind him, they were like, "I'm here isolated. I haven't seen a girl in like 4 weeks at least. Just been seeing these screens." And there was like, within 2 minutes, I shit you not, there were 5 girls who were just entering that building and exiting, like super hot as well. I was like, what the hell is going on? So we invented the BPS score, babes per second. But anyway, guys, let's calm down here, okay? Let's calm down. No. I have an awesome X0. Yeah, X11. Yeah. I also thought about that today. It was pretty fun. Yeah, exactly. Guys, I have so much to talk about today. It's like, I don't know how we're gonna do this. It's gonna be a long one for sure. But here's the thing. So the purpose of this stream is to summarize a lot of the developments that have taken place in the last era of time, and hopefully make it comprehensible, because I want everybody to follow what we're doing. It's insanely mucho. Jack has a 96 core brain, and all of them are running at full throttle right now. So the Jack percentage is like 100%. So, but I want to start to talk about some blockchain structures in general, so you have a framework to put all of this data and also pinpoint some problems with other chain. So I want to start with that. Then we're going to go full degen into mining XenBLOCKs. Number go up, go technology, because especially if you're new, and very confused about what we're doing and how to go about proof of work, this is going to be super alpha for you, and it will simplify a lot how to think and what to do. Because proof of work is new for me too. I never really did proof of work. I just never did it. I was in the proof of stake world, so I've learned a lot the last couple of weeks. Like I really went deep into trying to understand what it's all about, and so I think I can bring some value into letting you guys know like how simple it really is. It's not more difficult, but you have to know what to look for and how to comprehend everything. Hopefully it will be valuable to all the more senior assets as well. The rest is just going to be like hours of tech, like nerdiness, talk about consensus mechanisms and peer-to-peer network, a lot of focus on that, and show you guys a lot of the tests we've done and stuff like that. So it's just going to be like pure tech talk for a long time, and self-custodial hashing, some open source protocols that we are utilizing for this project, like Quick and the peer-to-peer, go through the tests, peer-to-peer broadcasting and propagation to probabilistic consensus. Say that 10 times. And transactional properties, block production, active coordinator rotation, and participation flow chart. And then we're going to talk about Solana and how great they are. Harry, how will all of this translate back to Zen? Jake mentioned everything is Zen. Everything is Zen. First principles takeover, baby. That's what it is. Everything is Zen. So that's how we do it. Let's see, where are we? Oh yeah. This is also This is also like if you go to a party this weekend and you want to impress a girl and she asks what you do, you tell her this: I'm building a monolithic or semi-modular asynchronous delegated proof of consensus and parallel block production blockchain with probabilistic consensus and memory hard cryptographic hashing algorithm to mine Xenium with self-custodial hashing and social consensus of being a hashhead. so that's what we do. I don't think this makes like any sense to you right now, but after this stream, it will make perfect sense. So try it out. Let me know how it goes. I want the ratio of success. I think it's gonna work like 100% for sure, 30% of the times. We can always work on the pitch and iterate it. But anyway, guys, I'm just gonna head straight in because there's a lot of info, so I'm not gonna hold back. Nothing of it is time sensitive though. So girls are going to be squeetering. I don't know what that is. You have to teach me how to make a girl squeetering, Profeta. Yeah, hit the like. So yeah, but I'm there's nothing time sensitive. So like chill out. I can always just split this up. There's a lot going into this because the speed has been so insane. As a Finnish rally car driver said when he was going too fast in a corner, the speed was good, but the corner was too tight. So yeah. Blockchain structures. Okay, since we are now creating infrastructure, I think it's important to cover some basics of blockchain structures so we get on the same page, because it can help you understand what we are trying to solve in the first place, and it will give you a framework of all the data that we will go through next. So there are two types of blockchains. You can compartmentalize them into different categories. So it's monolithic and modular. So monolithic blockchains, they feature a single system architecture in one layer. Okay, so like Bitcoin or Solana, you have execution, settlement, consensus, and data availability. They're all served in the same layer. And then you have modular. They're more adaptable. So they're specialized, they offer more flexibility, and modularity really refers to breaking down a blockchain into smaller independent components that can be easily replaced, upgraded, or extended. But for modularity to be achieved, you need to balance trade-offs between scalability, security, and decentralization. So we use our famous blockchain scalability trilemma, and we use that as a model to enter this stage of thinking. So in number A, you have decentralized blockchains who also tend to be secure because and this is why we like decentralization, because it's unlikely that one single party or a small group can manipulate the blockchain, and the consensus therefore is also robust in a decentralized secure chain. But and Bitcoin is a very good example of this, but they may suffer, on the other hand, from lower throughput because of risk of lack of scalability. So we see this with Bitcoin, and we see this with Ethereum. So that's why we are trying other things. Number B, so generally, if a chain is scalable and secure, it's likely not decentralized because it requires substantial hardware, validator requirements, for instance, as an example, for faster transaction processing and communication. You need more expertise, you need more funds to run a node, and that in turn limits decentralization. And this, I would say, fits into Solana very well, added to the fact with their token distribution and things like that. And then we have number C, where if a chain is decentralized and scalable, so you can easily set up nodes, for instance, and operate to handle transaction and communication for consensus at a high rate, but the latency can result in delays in the communication, which in turn leaves open for attacks, and it can disrupt consensus and put security at risk. So chains have made these various trade-offs to find a harmony between these three corners, let's say. And the challenge, which is this model suggests, is to have sufficiency, I guess you can say, to find the right mix, the right balance between these three. And that's why it's also hard, I think, to find like an overall consensus over which L1 is best, because everyone has made more or less trade-offs on these things. And they can also be influenced, of course, with whatever use case the chain is really targeting, because sometimes the chain is targeting one specific use case. So we see with Bitcoin and Ethereum, they have high gas fees, slow transaction confirmation times, and therefore also slow finality, which is a feature and a bug, but it leaves it open for other solutions. So with Bitcoin, you have also block reorgs, transaction confirmations are produced by the miners, and they are slow and they are expensive. So you need like a whole network to agree for confirmations to happen on Bitcoin. With Cosmos, Solana, and Polygon, you prioritize the transaction execution time at the expense of this data immutability. So Polygon relies on transaction settlement on Ethereum. Solana, they are fast, but they have stability issues and excessive consensus validation chatter and expensive hardware requirements. So we're going to talk about that today. But the point is, the design and the architecture of the chain is absolutely critical. So we're going to break down this architecture in the concept of modularity. And this is the components of the blockchain stack. So we have these 4 layers, and every chain needs to either handle all of this 4 components inherently, as in monolithic chains do, or they need to be plugged in to another system that handles parts of it, let's say. So in the execution layer, you need to be able to process transactions between states. So in this layer, users engage with the chain by signing transactions, executing smart contracts, and transferring assets. The settlement layer is this layer. You ensure the transaction immutability, so no one can alter the record, the transactions, the recorded transactions. So settlements provides finality and irreversibility. So you must validate transactions, you must confirm proofs, and you must have a way to resolve disputes when they happen, because they usually happen in one way or another. So how do you then solve that? And then we have the consensus layer, and this is the process where you establish an agreement of validity of the transactions. So you create a system for how to order and how to manage the finality in a network which is full of nodes, and you download, and all these nodes need to download and execute the block content, let's say. So all these nodes, they collaborate to reach consensus on the validity of state transitions. We'll talk about this today, how we do that. And then in turn, it determines the whole network's shared state at any moment. And then we have the 4th layer, the data availability, which is the process to ensure access to requested data within the chain. So block producers, and in our case, what we call block proposers, they must publish the transaction data for the network peers to download and store and process. So this is very relevant for Xenium and XenBLOCKs, because that's what we try to solve, and delegated proof of consensus, where we separate the transaction confirmation with a proof of stake layer who produces blocks in parallel from block immutability with a proof of work layer. But as an example, like Alice sends Bob some Zen, and the smart contract that handles the token transfer, in this case, it's executed in this execution layer, in the execution component. The settlement component handles the finality and immutability of that transaction. The consensus component makes sure that all the nodes agree on the validity of that transaction. And we have the data availability component is responsible for storing the transaction data for its completion and providing the infrastructure for all of the above to even happen on chain. So again, this happens for all blockchains. In monolithic chains, this occurs with all 4 components in a unified blockchain stack. And in modular chains, you assign different components to various chains. So if we look at monolithic chains in particular, all tasks are carried out on the single ladder. So nodes in a monolithic chain, they're responsible for executing consensus, ensuring data availability, and validating the transactions. So for example, in Bitcoin, like the first ever monolithic blockchain. So in Bitcoin, it requires nodes to process every block using their own local copy of the chain. So nodes are computers within the network, and they're responsible for validating and relaying these transactions. And this is great for Bitcoin security and decentralization, but of course, it makes it very challenging to handle high transaction volumes and accommodate more user. And this is exactly what we saw with VMPX when we launched it, because we know this better than anyone because we tested the chain to the max, as we always do with the launch of BVMPX. So at the launch, we saw that the sats per virtual byte went above 600, which is the first time in history where miners got more paid for on-chain transactions than block rewards, which is pretty significant. And this is the reason why also ordinals are super interesting, because it opens up this whole new world of use cases for Bitcoin, as we were very early to point out. And you know, you have Michael Saylor. He's really pushing this ordinal narrative right now, because it is, as he says, like miners, they need to get paid. And at some point, I'm also convinced that transaction fees will be higher than block rewards on a regular basis, like rather sooner than later, like when the world catches on what ordinals can do. Like there's a minority within crypto who still are trying to grasp what the tech really. They should just watch like syndication, like that stream I did just like clearly states the video about Bitcoin ordinals like 6 months ago. It just tells exactly how it works, but it's going to take some time for people to realize that. But the thing is, like, the more demand for block space, the more transaction fees there will be. So that's the relationship. So yeah, it's kind of cool that we were the first ones in history to plant our flag, our fang, our fang here with what we did. So VMPX has a good story that will last in time, I think. Now we have like what is it, like around 40 million inscriptions, and we started. There was like sub 100K, I think. Jack and I started playing around with it. But the thing with this is it's interesting how it is going to scale, because people want to do things with Bitcoin now more than ever, and it's only going to increase. So for example, how do you create a DeFi environment on Bitcoin? And if you take BRC20s as an example, so you can either settle on the base layer like Unisat does, which is great for their security in the sense. But by the way, I just tested their new BRC20 swap, which is super cool. I provided some liquidity for VMPX to test it out, and I love Unisat. I think they're great, and they're awesome for this space. But as a solution, you also have to be honest and admit, like, if you're coming from Ethereum and you're used to being able to get like instant, more or less, not instant, but within 20 seconds at least, a confirmation. It's pretty pain to have to wait like 1 billion confirmations for like 2 tokens and a third, because they're using Sats BRC20 as the gas token on the swap. So it's like the fact that they have this huge confirmation times and that only to like provide liquidity, which we like see as something that is like liquid. It should be able to be done fast, right? So that means there are going to be L2s that will attract like users because they have a USP, which is you can settle indirectly on Bitcoin, but you can have super fast, lightning fast confirmations, like Libra is trying to do with their BRC DEX. So you're gonna have a demand for a better trading environment, but then they have other trade-offs, of course. But people will want to settle on Bitcoin no matter how they do it, no questions about it. Then we have on Ethereum, of course, our home arena, where Vitalik is the papa. So on Ethereum, at its current state, let's call it they're using SATs as transaction fees, exactly. So so you have to get sats. So it's pretty cool in that sense. You have to get sats in order to be able to provide liquidity in the first place. But then you have to also wait for those transactions, and then you have to, as you know, with ordinals, you have to inscribe transfer first. So you have them in the wallet. You have to inscribe transfer, wait for that confirmation, and then you have to provide liquidity, which is another round of confirmation that needs to take place. So it's a very like strange to do so, but I think it's going to be interesting. But anyway, on Ethereum, on its pre-sharded level, and they will probably never shard as well, so they can be considered a monolithic chains where the L1 handles everything. So in a sense, I'll get into that later, but with Ethereum, it's secure and decentralized, you can argue for, but they also can't scale because you have 10-second block times, you have 30 million gas limit, and you have so it's 30 million gas limit per block, and you have, as with Bitcoin, sequential block production, right? So these three together makes it very hard to scale. And of course, we know better than anyone these limitations of Bitcoin, because gas fees are like way too high. And Seniors know this very well, because Gwei was like 5 a few weeks back, and a few days ago it was 255, and right now it's 52 or something, and we're just starting like a bull market. So you sort of have to think twice with Zen in that environment for either claiming your mint or minting more even, which is great for the supply of Zen, by the way, but that's the sort of like gas game you play with Zen. So what happens then in a bull market when Gwei is over 400, we can see here, this was the last bull market. So here you have the scale as well. So Gwei 400. So let's assume that it will be higher this year, so to speak. So what happens then with Gwei in that environment? Like bye Zen supply. But everyone agrees that the gas fees are a problem for adoption. So additionally, Solana is a monolithic chain that unifies this execution, data availability, consensus in a single layer. But in contrast to Ethereum, Solana provides scalability. So although validators validators have to have a pretty high hardware requirement in order to do so, to process this thousands of transactions per second. So for the validators, for the validators' votes, basically, that's what they process. This is what we'll talk about today, which is insane. We question whether they really can scale, and which is interesting. But the point is, with Bitcoin and Ethereum, you have limited amount of block size, you have limited amount of time per block, and you have sequential block production, which Solana also have. And then we have to realize, okay, if this technology is going to adopt, you have 8 billion people who wants to transact on the chains. So something has to give, like it can't scale. And then you have Lightning Network, you have L2s and other chains who have made things a lot better, but they also have made their own admin key trade-offs or whatever they do. Anyway, so then we have the layers of the modular chains. Okay, so the modular chains, and they are composed of, you can see them as like interconnected modules. Okay, it's all Lego components who are responsible. Each component is responsible for specific functions. So the setup is more like streamlined. It's flexible, it's scalable. Each module can be optimized for handling just a specific focused task, and they're part of a larger modular stack. So one module delegates the rest of the functions to other layers or other modules. So you can see them as like pluggable modules. So then we have rollups, which is the most popular, like smart contract rollups, we can call them. So you have Optimism, Base, Arbitrum, ZK Sync, and a whole bunch of others. So these L2s, they're focused on scaling the monolithic underlying L1 Ethereum, because the underlying L1 Ethereum can't scale. And they are like an extension of the L1, acting as an extension to like increase their throughput, their TPS. So rollups can act as an execution layer while depending on the base layer for other functions such as data availability, consensus, and settlement. Then you have Validium chains. So they are a rollup variant to process transactions off-chain before submitting them to the parent chain. And then we have sovereign rollups. So Celestia is a good example of that. So where transactions are published to another chain for ordering and data availability, but it has its own nodes to verify the transactions. So a smart contract rollup, like Optimism and all of these, a normal rollup, transactions are verified by the smart contracts on the settlement layer on Ethereum. But with the sovereign rollup, the transactions are verified by nodes on the sovereign rollup itself. So it's a self-sovereign thing. It can take care of itself in that aspect. And for Ethereum, it's interesting. I don't know if you read Vitalik's latest speech to the Crypto Nation, because it's becoming more and more clear that L2s for Ethereum is like getting more traction and focus than Ethereum sharding and scaling the base layer itself. That's at least how I interpret it. So what does that mean? And with this definition, it's kind of like a schizo how to categorize Ethereum, because is it a monolithic or is it like a semi-modular chain? So on that, you then have like a spectrum of how to categorize these chains, which is also important, because here we can see how we can look at these other chains. So you have the monolithic ones, Ethereum, Solana, also Tron is there, Cardano. So these blockchains, they handle all the four components of the blockchain duties, you can say, on their own without relying on any other party chains. And we have modular, like Optimism and Arbitrum and ZK Sync and Celestia Base. So they are built to handle specific tasks, and then they outsource the rest. But in between, you have also the spectrum. So you have so-called polyethic chains. And these include Cosmos, Avalanche, Polkadot is a good example. Because these blockchains have a multi-chain architecture composed of a base layer, which multiple heterogeneous and homogeneous blockchains, you say. So they split a single network into multiple parts with sub-networks that are dependent on the single network. For instance, Avalanche, you have C-chain, which its purpose is to handle smart contracts and EVM smart contracts. You have P-chain for coordinating validators, and then you have X-chain for creating and exchanging assets. And then you also have the semi-modular. So let's say that Ethereum includes there after sharding, if they ever get there. Like Near and Tezos. So these chains blend their core functions with external systems with specific tasks. So in simpler terms, they manage some operation in-house and delegate others to specialized networks. So yeah, so semi-modular blockchains, they can still execute transactions independently. They can process and validate transactions within their network, but they can also outsources. Now, what's the conclusion of all of this? So the conclusion for us is Joseph saying something here. When Joseph speaks, we shall listen. Ethereum sharding is cancelled. They are testing proto-dank sharding, also known as EIP 4844. So yes, they're moving forward towards L2 world. The real dank sharding, 100K per transaction per second, will take years to implement. Yeah, exactly. Awesome to see you here. Vitalik, the luminescent alien boy. Yeah, he's also alien. Jack can speak to him. So yeah. What is our like conclusions with all of this? Like, adoption is still at 5%. So here's the thing: nobody has figured it out. It will feel like that. It will feel like some chains are way ahead than others and will be the ultimate solution. They may be, but they also may not be. So all of them have their limitations. Everyone, and every chain is so it's either with the, if you look at the blockchain trilemma, right? It's either a trade-off of decentralization, security, and scaling. But you can also look at it like the interplay between like community and team. Are there VCs? Is there funding? How's their tokenomics? We talked a lot about that, and we totally like discarded the whole space for their pie charts. So what we try to do first and foremost is something innovative that no one has done before, and because that's how I feel, and I think that's how Jack feels. Like, otherwise there's no point. But to do that, we have to like twist and turn everything. So that's why it's also hard to give like a roadmap, because if you want a roadmap, you should just go to one of these VC projects. To be honest, like, and also another thing to say, it's all Lego. Like, when we build chains, we have to know what we're trying to solve. Like, what are the trade-offs we make? And are we creating monolithic or modular? So how are we handling execution, settlement, consensus, and data availability? So yeah, we go through like very deep research, both in theory and practice. And we're studying a lot of other chains, and we're testing our own concepts. And we're taking this concept, because the thing is, like, it's like taking raisins from all the different cakes, the best cookies, and then you have all the raisins, which doesn't make sense as an ideology, because like then you just have raisins, but you want the cookies. So we take the cookies from the raisin cakes and we leave the raisins anyway. But yeah, then we will see how we do with the X1 EVM engine, or let's see if we can call it X1, maybe X69. I think for some reason it will fit into the whole Pussy.io narrative as well. But anyway, we like proof of work, and we think it's great for security as a base. But and yeah. But the most important thing out of all of this is, I want you just to have this framework in your mind, because when we talk about like XenBLOCKs, it's important to think about how we compartmentalize like all the abundance of data that I'm about to hit you with. Like, what are we talking about? Like, how does this fit into a bigger picture? So this is like a good foundational model. And I think also like a semi like conclusion really is that if you have like limited block size, like if the block size is limited, the block time is limited, and you have sequential block production, it's very hard. It's very hard to scale. So the model we propose here with XenBLOCKs is something that diverges from this way of thinking, because we have endured, my fellow friends, Sinians, my fellow vampires, my fellow hashheads. We have endured the limitations of the previous generations of chains. We know their limitations. Either gas goes through the roof, or they shut down, or they censor us, or they manipulate gas fees, not to mention any names. So there has to be a better way. There just has to be. So that's why we now are going to go deep into XenBLOCKs. Yeah. Here we go. So now we're switching completely like cores in our CPUs and focusing completely on XenBLOCKs. But this was just to give you like a framework to think about. So with mining XenBLOCKs, we're going to start with that, because I see many are still trying to grasp like proof of work and like how to go about it. And it seems very complex from the outside, but it's really like super simple. So we'll try to simplify it like a lot without like introducing any complexity whatsoever. So I think you can think like this: input and output. So as a miner, it's not more complicated than you have an input of either fiat or crypto. Like since you can pay GPUs with fiat directly, that's very interesting because there's no need to actually route through a centralized exchange. So you do some work, and the output of the machine is Xenium. So there's an input and output. So you put something in and you get something out of it. It's a conversion. I can't tell you like what the output, if that's going to be valuable or not, because that's up to the market and social consensus to figure out. And that's been kind of nice in this project because it doesn't have a market value. So people have just focused on the tech because we're in for the tech. And so that's an interesting thing. But what I can tell you is how to begin to think about in terms of optimization. So you're putting in dollars or crypto and you get Xenium. So as in any production process, you want to minimize this and you want to maximize this end. So how do we do that? So let's dissect this proof of work for what it really is. So let's scale this model up a bit. Can you see it? It got very small. Yeah. Okay, yeah, I shouldn't have done that. Maybe I can make it a little bit better. Okay. Yeah, but let's take it part by part. So yeah. So here's the process. You have some fiat or crypto. You need to rent or buy a GPU. You need to have a script and to run on the GPU that will produce you hashes per second. And so you know what hashes per second is by now if you follow my stream. Like it's you see it as guesses. So your miner creates a key, and then the cryptographic hashing algorithm Argon 2 will guess and guess and guess and guess again for a solution that matches this key. So 10K hashes means that you're guessing 10,000 times per second. And it will then find a XenBLOCKs, which will yield you Xenium. Okay, so that's the process. So let's break it down. Now, here, XenBLOCK to Xenium, this part of the process, this is fixed. Okay, so this is fixed according to the inflation schedule, if you like, with yearly halving. So we have something that looks something like this, right? Okay, so this is not something that you can optimize right here. It's the same for everybody. Nobody can do anything about it. It will be adjusted to incentivize miners to also run nodes. More on that later. But there's nothing anyone can really do about it in terms of optimization. And then you have hashes per second to XenBLOCKs. So it's the same here. It's the same rules for everyone. You can't optimize. It's just numbers, the numbers game. The more hashes per second you get, the more likely you are to find blocks. And then we have the script. So it's pretty binary in a way. Like if you deploy the script, it works or not, and everyone is more or less using the same script. But there's like two things to this fundamentally. It's like get it running properly, and to be safe, I'll just use Joseph's script, the one-liner. Well, I talked about that last stream. I know people are trying to make that process better, but the process I showed you last, step by step, that pretty much still holds. That's the process I still use. So if you have any issues understanding each and one of those steps, you have 2,000 hash heads that will go in the Telegram and tell you exactly how it works. But the other thing you want to check for is like maintenance. So it's like your garden of machines. You have to take care of them, and over time, like to make sure that they are working properly. So GPU percentage is like the first thing to look at, and also over time, because it can also decrease. So that means that there's something wrong with the machine. So that's the most important thing. And they're more or less best practices how to handle those situations. So this is what I do. Just a glimpse of an example. I just go in terminal, log into the GPU, and I run these commands one by one. To just clean it, wipe it out, and then deploy the script again, because there's no there's updates of the packages, and there's no conflicts. That's worked for me in 95% of the cases. So it can also be that the machines are just there's something other wrong with them. I wouldn't waste time. I would just go with if this doesn't work and it's still not producing GPU percentage, which should be above 90%, then you're good. If it's below 90%, if we're allowed to generalize, there's something wrong with it. I would just focus on getting another machine instead. Yeah. So yeah, and then you just rerun the command. So just screenshot this. But the important thing for you to think about is like having a GPU. It's like a gardening thing. And the other thing is that has a significant impact for your output is whether you should rent or buy a machine. Okay, so let's break that down. And for you to be able to think about that, you got to get to know the machine first. Okay, you got to feel the weight of the hash. Okay, you got to know the ins and outs of the machine. But I would say this, like first we can talk about the performance of the machine. So some GPUs, they're very well suited for hashing, like with Argon 2, and some are not. So here's a list of GPUs that work. It's a longer list, but if you're new, you should just focus on these. They work. So when you go and rent one, which you should if you're new, focus on any one of these. You can just screenshot that. But that's the first thing to think about. And there's yeah, that's what I would say to make it easier. So probably the most important aspect of that is to get insights. It's not a matter of getting the most expensive and performant machine. Let's put it like that. It doesn't matter for us, because what matters is what the GPU can do for us in relation to what we have to pay for it. Okay, so that's the trick. So the A40, for instance, it's one of the better GPUs that generate a very high amount of, in the mid-range section, a very high amount of hashes per second. However, if you have to pay $4 per hour for it, you're better off getting a RTX 220 that generates half of the hashes per second, but it's 4 times cheaper. So I'll talk about that next. The other thing is, if you should rent or buy, I'd consider these things also. Like with buying, you have this upfront cost, which is the trade-off that you will in time get a lower running cost, because you only have to pay for electricity and not have to rent for something. But you also take more risks, since it's a highly rapid evolving project, and since the cost saving only comes with time. So there's no guarantees that you will be able to use GPU to mine XenBLOCKs in the future. Like some people rushed in to buying CPUs until the code was cracked by Woody to mine GPUs instead. So those CPUs then made you can still mine with them, but they mostly made some kids very, very happy because they had a very cool gaming computer in relation to their friends. But for every day, I'm getting more and more convinced that GPU is here to stay. But just to be aware, there's a risk, even though it's minuscule. But I will talk about that a lot more when we talk about Argon 2. So the other thing you can do is renting, right? So now you have a fixed cost. You have no fixed cost, no upfront cost at all. So you simply pay by the hour. So you rent with one click, and you can terminate with one click as well. So it's super clean, it's super easy, it's low barrier. You don't need to know how to plug in the goddamn thing into a motherboard. You don't need physically maintain it. You don't need to. You graphically be locked into one place to maintain it, which I love. So you do everything in the cloud. And the only downside is that you, with time, probably will overpay versus those who have their own machines. So what also influences this rent versus buy is your lifestyle and your nerdiness. So for me, I travel all the time. And I do so because I have to run from the feds and all the hot girls who are chasing me all the time. But if I was stationary in one place and I had IKEA plants I had to water every day, then I would definitely buy a GPU, because it's a lot of fun to learn. So there's other values influencing this as well. It's like being able to and this is why I love proof of work, because it's like a physical thing that you can play with, and you're in full self-custodial control over your mining process. It's not just like some proof of stake thing where you just click a button. Point is, renting versus buying, super individual. But if you're new, you should like rent 100%, because, and you do it from vast.ai, vast.ai, runpod.io, I think it is. Please correct me if I'm wrong. Joe Blau is in the house. Joe Blau is in the house. Good to see you, brother. Good to see you, brother. Anyway, but there are also people in the community who are looking into like providing, because we have both internally in the community, we have both the supply and demand of the whole process. So Vast takes 25% from the supplier of the machine. So there's like a huge savings there that we could have in the community. I rather pay it to a hash head than Vast, to be honest. But anyway, so the proof of work can really be like zoomed in to these parts, and that's pretty much it. Like, it's that simple, really. So and just as a like but okay, here comes the other thing that's very important, because what's beautiful with all of this is that all of this whole production process, this whole factory, can be measured in just one very key metric, which is hashes per second per USD. So you take basically the output divided by the input. So if the number is high of this ratio, that means you're doing all of this in a good boy crypto kind of way. Okay, it's as simple as that. So that's what's pretty cool. It's just like one metric to compare everyone's work with, because you can analyze this in a binary way. Like, if it's high, then it's good. If it's low, you're doing something wrong. So there's, as a reference, like with the current difficulty of, what is it, like 90K, you should at least get 10K hashes per second per dollar spent. Okay, because if you're not doing that, you're paying way too much, or the GPU percentage is low, so it's not producing enough hashes, or there's something else that's wrong. So the ratio of hashes per second per USD is really just like the input versus the output in the proof of work that you do. And in there are things you can affect versus not, in order to maximize the output and minimize the input. So it's as simple as that. But now, okay, now comes the like that's the basics. But now, if we want to like really optimize this, it leads me to the next point, which is like BI systems, and this is one where, because like your biggest problem now when you're at this stage is, now you have a bunch of GPUs and a bunch of machines and a multitude of metrics to keep track of. And it's insanely time consuming, and it charges brain power, and you go and check them like multiple times per day. And you don't want to do that with time. It's fun at first, but then you're like, okay. So there must be a way how we can automate all of this analysis, and there is, because you want to get in a situation where you can just, with the click of a button, get the overview over your whole machine park, and see their performance, their cost, and their performance over cost in time. So this is why I really love the performance bot made by Traveler in the community. I've tested it. I think it's awesome. It's super good. You just run the script in your terminal. It plugs in to your Vast account with your SSH key. So it fetches data from your Vast account in a secure way, and it creates this table with all the data you need for maintenance. So what you have here, first you have your balance, so you can see like how much you have in your Vast account. So you have that. So the total balance, the spend rate, based on the current machinery, like how much will that cost you per day, and based on that, how long will the balance you have last. So that's just like super nice data. And then you have this like summary data. So you have the difficulty, you have the total hash rate from all your machines, the total dollar per hour this cost, the average amount you're spending per block, and the total blocks per hour that you're producing. And these are pretty cool metric over time to sort of like measure against yourself to see that you are they are producing as you want. And if you need to do some upgrades, it's totally individual, but that's pretty good to look at. Then you have all of this data. So here you have the instance ID, which matches. It is the one that you have on Vast, that ID number. You have the GPU name. You have how many GPUs you have in that instance. The GPU percentage to make sure that here's something is 0. We need to look at that at the end. The dollar per hour, dollar per GPU, so it's divided by the instance, etc. This is my favorite, and in the code there are some customizations. You just need to open the code and change. I sort on, I forget now, but I think it's like column 10 or something, because I want the worst performer. It's done here. This is hashes per second per USD. Okay, so this is the most important one. I want the worst performer to come at top, the worst offender, because that tells me, okay, this is the one I need to take care of first. So that's pretty awesome. You can also put a label to it, and it also gives you this report saying right down here, so you don't even have to work through this data up here. You can just check. I always think you can see my mouse, but at the bottom of this table, it says a warning saying GPU for this instance is at 0%. Make sure the send GPU miner is working. And you do that by the process that I showed you before. And then it also gives you this deviation report, which is pretty cool. Google Z-score, what it means. It's a statistical score, and you can set that, customize that value as well in the code. But it tells you that for this machine, that this machine is not performing. It's performing further away from the deviation I'm okay with, based on the Z-score and the other machines. So it will let me know. But anyway, I think it's great. This has saved me like huge amount of time. I use it every day. I just go into terminal, I run this script, I get the table, and it just gives me this raw data that I want. I analyze the table, I take the actions where it needs to be. It does all the heavy work and that I used to do myself in the head, and I don't need to scroll through Vast. So that's awesome. Insanely well done, Traveler. Awesome. One of these hidden gems, really. I didn't know existed before, but he's been in the community since the early days. But this is also cool with it. So this is also cool with this project, because there's a lot of degens hiding in shadows. They're really strong supporters of what we do, but they've given a chance to contribute. So this is also like what's beautiful with this project. It's sort of like a development hyperstructure, because Jack created this miner, and then Woody cracked the code how to take this miner and use it for GPU mining. And then Joseph came in and did all of that much simpler with his one-line script. And then you have Traveler came in, and a lot more with the BI system to analyze all of it that goes on. So it's super fun how the community has been involved in like creating what we have now. That part has been super fun. So keep creating cool shit, you fucking hashhead. I love to say that. I hope you don't mind, just a little bit. But anyway, so yeah, if you're a hash head, if you're mining, you're a hash head. Okay, so if you where's the script? Link to the script. I mean, it's Joseph's one-liner script on Joseph's GitHub. Joseph, if you're still here, it's Joseph's GitHub. It has instruction exactly what to do. I went through it in my last stream at the beginning, like the process step by step, how I do it. But anyway, the definition is this: if you're mining, you're a hash head. If you're also contributing and building cool stuff, you're a hash head hacker. So you're a triple H. That's the definition. But anyway, miners, they are important for securing the network, and we want to make it comprehensible for as many people as possible. So like fear of even trying, because it's a bit more work than just sitting on your fat ass as deploying funds with a stake pool. You know, it's this is important because how we collectively break down every little detail about how to perform this mining is very important. So, and teach new people about it. So we need to make it way more easier for people to do so. And people who don't understand need to go in and say, hey, I don't understand how to do this step. So we need to help them. I think CryptoBro does amazing streams. Tree City West, he also made an Explorer multiple times a week. So if you like that, you should follow them. But guys, that was enough mining for now. Now we're gonna talk about Argon 2. Now, so from now on, it's just gonna be like more tech. If you don't if I mean, yeah, that's also needed, I guess. Oh, the performance script. Sorry. Yeah, good question. You go into Telegram and write. I've set up some bots so you can just do this hashtag performance in the Telegram, and you get the link to Traveler's scripts. Sorry about that. Yeah. Anyway. Yeah. So yeah, from now on, it's just going to be another couple of hours of pure degen tech talk about how this all works with all what we've done the last couple of weeks here, because it's been pretty substantial. Jack's completely nuts. It's been pretty cool to see. But what I want to talk about is Argon 2, because it's at the base of what we are doing here, really. So Argon 2, en enkel 2. So what I want to talk about is how Argon 2 relates to memory and difficulty, because it's key, and I want to break it down like in detail, because let's start with this. What is Argon 2? So Argon 2 is the cryptographic hashing algorithm that we use to mine XenBLOCKs with. So it difficulty adjusts the requirements shared with all miners. It's GPU and ASIC resistant, okay, by nature. And resistant doesn't mean it's technically impossible. It means it's harder. So it will cost you more. It will be more difficult. And here's why. So it is so because it requires a relatively large memory, VRAM allocation. So this makes the hash speed reduce as difficulty moves up. So Argon 2 is a memory hard algorithm, and memory hard algorithms are linked to memory and RAM usage. So what is memory? Let's break it down in Levin's. So memory, it's a component in your computer that stores data while the computer runs, and this data can be anything from a Word document or to a website you're browsing right now, watching this. So when your computer needs to access this data, it does so very quickly and easily from its memory. So then what is VRAM? So VRAM is a type of RAM. So while RAM is the general memory of the computer, it's the memory your processor uses to store data on which it's currently doing some computation. Because you also have storage, hard drive. VRAM is a portion of RAM that is specifically dedicated to processing graphics related tasks, and GPU is a graphics processing unit as well. So VRAM is the video RAM on which the graphic processor stores data on which it's doing computation. So a miner, so as a miner, you need hash power, you need hash, man, to give, and that is what the GPU is giving you. So GPU is the graphics processing unit. So it's designed to accelerate the computer graphics and image processing. But it also turns out that they are amazing to mine XenBLOCKs with. So you can get a lot of hash power with them. So to produce one block of one XenBLOCK, you need to access memory. So you need to access VRAM. And this means that you're now limited by the VRAM speed. So the amount of time it takes you to access this memory, the bandwidth, the data transfer rate, that's significant, and it drives the difficulty, not how fast you find the blocks. So this means that the speed of VRAM is the limiting factor. So for example, if we now have like around 90K difficulty, so that's very close to 100 megabytes of data to produce one block. So for you to access 100 megabytes of data to produce this block, it will take you X amount of time. Now, if the difficulty moves up to 200,000, so for you to access 200,000, for 200,000 difficulty, you need 200 megabytes of data. So that will take you, instead of 100 megabytes of data, it will need 200 megabytes of data because the difficulty is higher. So that will take you twice as long to produce that block. So it's not exactly linear, but just for the sake of argument. So your hash rate is controlled by the bandwidth and not your ability to solve hashes. So as the difficulty moves higher and higher, you need more bandwidth to produce the block. And this is why Argon 2 is what they call a memory hard. It's you need the memory access that is not unlimited. So the speed of VRAM is the limiting factor. So what is the speed of VRAM? And here's a table that outlines different kinds of. So we have RAM type speed and transfer rate. Okay, so DDR4 is like top notch in VRAM, and they produce around 25 gigabytes per second. That's how much they can process. So if we calculate, let's say for sake argument, let's say the best we can have is 20 gigabytes, just to make it easier. So that means to produce one block at 90K difficulty, it requires 100 megabytes of data. And one block at 200K difficulty, you need 200 megabytes of data. So if we take 20 gigabytes per second divided by 100 megabytes of data, you can see it as you can fit 100 megabytes into that memory 200 times per second. So you can load 200 sets of 100 megabytes per second. And in the same case, if we take 200 megabytes, which was the 200K difficulty, you can fit 200 megabytes into that memory 100 times per second. So you can load 100 sets of 200 megabytes per second. So with a high-end GPU, you can do like, let's say 5,000 hashes per second. But it's very hard to make more than that because the memory can't handle more. So you can't have unlimited hash rate and dump it on memory. So the speed of RAM, it doesn't allow for terahashes. So even if you had unlimited RAM, accessing 100 megabytes won't allow for such speeds. Now, this is different from Bitcoin in the sense that the hashing algorithm there is SHA-256. So to produce a hash, it's around 64 bytes, which is nothing. It's not even a megabyte. So we use 100 megabytes at 90K difficulty because the algorithm needs to generate first. So why do we require 100 megabytes when Bitcoin only needs 64 bytes to generate one hash? That's because the memory requirements is different for between SHA-256 and Argon 2. So generation takes time, sending takes time, and compute takes time. So think about like hash power. It's not just the hash power you need. You also need memory. So even if you had unlimited hash power compute, as long as you have limited memory, you can't produce blocks fast enough. So Argon 2 is pro-douche, exactly. Are you pro-douche or pro-not douche? Huh? That is the question. Are you pro-douche or not pro-douche? Where was I? So yeah, you can't access, you can't produce blocks fast enough. So Argon 2 is memory hard. When difficulty goes up, memory also goes up, as we talked about in the last stream. So memory is the limiting factor here, really. And that's with ASICs. And this is why ASIC mining is very likely to succeed until someone proves me wrong on this. Because it doesn't matter if you have the best mining calculation. You still have to link to memory. And memory takes time to create the data structures. And that's what makes it resistant. So then it's like the nature of memory being slow versus chips. That's the battle inside your computer machine. But then you say, yeah, but okay, with time, memory can shoot up in speed and developments, and it becomes faster. And this is interesting because the thing with ASICs is that they are very specialized machine. They perform very fast calculations, computations. And Bitcoin miners, they use them to mine Bitcoin, and they use them for like 1 year, and then they have to replace them and to stay competitive. But nobody needs ASICs. It's only select few. So it's very specialized machines. Memory, on the other hand, everybody needs memory for everything. Like all of you watching this right now, you have a memory, like 5 memories within your periphery of being, within your aura. So time, so even though that makes memory can never be specialized in that sense, and the speed of memory the speed of memory will go up with time, but not by a multi-factor. So it's what Jack also says. He knows this stuff so well. It's so cool. It's the only thing in the silicon and semiconductor world, as he says, which you can't really optimize in price. You can build your own, but you can't, and you can find a better distributor who gives you a discount or whatever. But it's not going to be an 80% discount, because the RAM market is pretty much saturated, or not saturated, but that's the wrong word, commoditized and settled. So every other algorithm that is not memory hard, you can just build specialized hardware like ASICs for Bitcoin. So Argon 2 is memory hard. You can't optimize on memory. And this is why Jack chose this algorithm, which is memory hard, because specialized hardware can't be used because it will need more memory. and it makes the whole mining process like way more fair. So it's pretty cool. So on that, like if we want to dig further, there are some like special high-end GPUs, like the H100, which is totally nuts. But it costs like 50K, but it doesn't give you 100 times more memory. So a $500 USD GPU, which you can just rent on Vast, the mid-range of GPU is like the sweet spot. So 3090, 4090, and all of those I showed you before, over the high-end GPUs. And cloud mining is super accessible, so it works perfect. You can rent a GPU for 5 cents per hour and mine XenBLOCKs using like even fiat if you want. So low barrier to entry yet again. And this is also interesting why it's important to follow like principles when you create stuff, because it leads you to this better solutions, I think. So yet again, what we need to ask is not the hashes per second per USD. So if a 4090 is $1,000 and it gets you 4,000 hashes per second, but if an ASIC or FGPA that's like 10,000 hashes per second, but it costs 8,000, it won't be profitable. And also what's interesting, like if you're from China, like there's a lot of unused GPU miners around the world. It's like a huge market who are just sitting like idle. But what's interesting with the Asian market is that mining all kinds of Bitcoin or cryptocurrency is illegal in China. So what the government does is they can see that this is what's been explained to me, and this is how it works. They can see that you have excessive energy usage production, and they will find you and they will stop it. But since the power consumption decreases with higher difficulty, it's very hard to get detected mining XenBLOCKs. But officially, I didn't say all of that. I just said it theoretically. The hypothetical Sensu just said that. But anyway, Argon 2, it's very interesting. It's a very good hashing algorithm. It makes the mining process way more fair. Argon 2 is slow, but we want it to be slow because we want the difficulty. There always needs to be some kind of difficulty when you're doing something. Okay, let's leave that. Let's go into self-custodial hashing, which is okay, let's do this. I like the name self-custodial hashing. It's pretty cool. Let's just mention, we're not going to go deep in it, but I just want to simplify it and talk about why it matters, because we talked about this before. But most proof of work systems, they have like 2 essential components. So it's the key and the hash. The weakness is that someone can intercept the blocks before the blockchain can accept them. Okay, so this means that if someone intercepts the hash before it enters the chain, they can alter the owner's address and assign it to themselves. So it makes attacks on the chain a lot easier, because you can then reorder blocks and take ownership. But this can't happen with us, because the only way someone can take ownership of your block is if you give away your private key, and you're not going to do that. So with XenBLOCKs, all mined blocks are signed with your Ethereum address, making the block stealing impossible. So the ETH address, it's very nicely packed into 27 bytes, which is nothing. So it doesn't cost anything, it doesn't tax anything, and it's hashed into the block discovery. So in the salt. So you know what a salt is. It's like an added password to the mining process. So when you mine with your ETH address, you mine with the ETH address as the salt. Bitcoin doesn't have salt in SHA-256, but Argon 2 does implement it. So with Bitcoin, the block is stamped, but the hash is not. So Bitcoin stamping could theoretically be intercepted. Now, to be honest, I don't think it ever has, but that's not the point. And you must you probably ask, like, what is this is a solution to a problem that doesn't exist, and that's true to some extent. But the thing is, it's a feature that is pretty cool with self-custody in mind, that is undoubtedly very secure. So we don't have to worry about interception of blocks later on in the process. And that's why it's very beautiful. So just to mention a little bit about that. But now we're going to talk about some blockchain technology in the in the matrix. So we're going to go deeper into like tech stuff now, which is pretty exciting. So before, like, we talk about execution, settlement, and consensus, and the peer-to-peer network, I want to mention two open source technologies that we have adopted for the data availability layer. So, you know, like, so we are here. I told you to have this model in mind when we talk about stuff. So, but now we're there. So as you know, like, data availability is very fundamental for everything else we do on top, and we have to go down to the roots of doing so. So, you know, think of it like this: you have a peer-to-peer network of nodes, which we're going to talk about next. They need to be able to communicate with each other. So we need a way to exchange data, and we need some way to control this. We need a controller. So the way we exchange data, the first part, is very fast, and then we use something called Quick protocol. So we could have used TCP, and I'm going to start with explaining like what TCP really is. It stands for Transmission Control Protocol. So it's one of the main protocols for the Internet Protocol Suite, and it originated in the initial implementation of the Internet Protocol. So therefore, you might hear it as TCP/IP. Now, how it works is it provides an interface for sending streams of data between two endpoints. So the data you're trying to send is handed to the TCP system, and that ensures that the data you want to send makes it to the other end in exactly the same form. So the TCP protocol breaks down the data into small packets, and these packets travel from router to router, as we can see here, through the internet. Sorry for the resolution. And then the TCP protocol then reassembles those data packets to its original state to the recipient. So I mentioned TCP because, so you know, like the OG way of transferring data. But instead of using TCP, we use something called Quick, which is a way to exchange data much more efficiently. So we can look at this. So Quick is also this so-called general purpose transport layer network protocol. So it improves the performance in this communication, and it does so by establishing a number of multiplexed, as we say in the industry, multiplex connection between two endpoints. So it uses UDP at its base instead of TCP, and UDP is user data protocol. It's another communication protocol for time-sensitive applications, used a lot in gaming and videos and stuff. But it's faster than TCP because it uses UDP and because it reduces the overhead in the connection process with the handshake, basically. But so what is it used for? It's used for more than half of all the connections from, if you have a Chrome browser right now, it's more than half of the connection from your Chrome browser to Google servers. And I think most other, like Bing and Firefox and Mozilla, whatever, they also use Quick. So it's become more or less like a standard. So when you're watching me right now, Quick is probably the messaging protocol used to transfer this data to you. It's very cool with these technologies because it's like we're using, like, we're interacting with tech every day, but it's pretty cool to learn about the different protocols that are handling the processing of data communication between us. So so you have it sort of worked like this in structure. So you have the the application layer, which you're using with the browser, with the HTTP. And Quick is then used as the security and transport layer with UDP. And then this data is transporting using IP, which is the internet protocol. So it's all protocols, really. And Quick is much faster than TCP. So this is just some tests where we can see, like, with the same data, same servers, the transactions per second is improved by 85%. So Solana uses Quick as well, for instance. So they had their own version first. They always need to create their own stuff to motivate all the hundreds of millions of dollars raised. But then they realized they could have just used open source tech here instead. So it's pretty cool how we're going about this project with XenBLOCKs, because we're using instead of raising funds and hiring a bunch of engineers, we're using a lot of available open source. We're open source nerds to create all of this technology. So that's how we do things. So Quick and lib peer-to-peer, which I'll talk about next, and WebSockets as well. They're battle tested, they work great, they're open source, and you know, we don't have to invent anything if it works great. So they also have communities who continuously contribute to their GitHub and stuff like that. So that's how we exchange data. And then we can talk about lib peer-to-peer, which is the data availability. Let's see, we're still in the data availability layer. So lib peer-to-peer is interesting because this is how this works. Because Quick is a way how we can exchange data peer-to-peer using that protocol. But how do we then control this flow of data? How do we make sure that all the nodes get all the data? Like, which nodes get what kind of data? How do peers in the network broadcast this data, and what data are they receiving? Because we need to send data between the nodes of blocks or transactions or verifications, etc. So how do we make sure to have a structure to control all of that? And then we're using lib peer-to-peer. So lib is for library, not for liberal. So what it is, it consists of a collection of protocols, of specifications, of libraries that to facilitate this communication between the network participants, or in our case, the nodes or peers. So this is how it works. Very simple. First, you have a topic selection. So peers subscribe to one or more topics of interest. Topic acts as channels or message categories, allowing peers to filter messages based on their interest. So we have a node, we have a peer, and we're subscribing to a topic. And then we have message publication. So when a peer wants to send a message to a specific topic, they publish the message to the network. So this means they send the message to some of their connected peers who are also interested and subscribing to this topic. So peer number one is subscribing to topic A. He wants to send a message that's relating to topic A. So it sends them to other peers that are also subscribing to the topic. And then we have message forwarding. So peers that receive a message for a subscribed topic will further propagate it to their connected peers if those peers are also subscribed to the same topic. So this process continues, and it's creating a so-called propagation chain. So here you can see that these peers are further rebroadcasting that message to other peers in the network. And this peer, for instance, he is not subscribing to that topic. He's subscribing only to topic B. So he doesn't get that memo. And so it creates this so-called propagation chain. And then we have the message delivery. So the message eventually reach all interested peers in the network, and peers can then store or cache messages for a period. And this allows late joining peers to receive a historical message when subscribed to a topic. Yeah. So we have this message where the propagation chain, like, continues until all the peers in the network have got the memo. And then you can also filter out based on what topics you're not subscribing to. So lib peer-to-peer is so-called gossip protocol. The nodes are like gossiping to each other. So and it acts as the controller in between nodes. So you can think of it like this. You can have channels where node asks other nodes to give them data, and that data goes into the channel. So a topic is like a channel. It's like a radio channel. So you can tune into different channels, and nodes are listening to these channels. Every channel has a name. The most basic setup we can have is like, you can have just one topic for the whole network, and all the data goes into this radio channel. So everyone gets all the data all the time. But you can also have like a priority topic that the network will listen to first. So you can have like an emergency broadcast channel. So it depends on what nodes we have and what nodes want to do. Like some nodes only want to listen to network size and participants. Some others want to listen to data transmission and also like do something with their data package. But that's basically how it works. So we just mentioned, like, we continuously like make updates with the messaging with this protocol. Jack opened up the hood and like made a bunch of optimizations to it as well. So like this is one issue we had, for instance, just to give like just to show you like how like you have the setup, but then you need to optimize it for your protocol. So the issue was that one node, he was requesting blocks. Okay, and every node in the network sent all the blocks to. They could hear the request. So if they also had that data, they would send it. But everyone would send that data, no matter how many times that data have been sent before. So like 20 nodes hear this request, and then they're like, hey, here you go. But this is a problem because then it created sort of a DDoS attack on the network. It's like too much chatter. It was too Solana-like. So how do you make it not do that? Like, how do you push the block in an efficient way where you don't have to flood the network instead of pushing it everywhere, because then it's too much noise? So the problem was that the network was moving around out of sequence blocks. So previous blocks that's already been synced and verified by the node was still pushed around. So what we did was the node was listening to the block height of the network, so it can see that the block height, like the total amount. I'm going to talk about that next. So the total amount of blocks that have been produced, basically, and it could see that, okay, the block height is a higher value than what I have. So then it calculates the delta what it needs. So the block height is 100, I only have 99. So then it will broadcast to the network, okay, I need only block 1 to be complete in my node. And then someone responds to it and says, hey, I have this. So I have this and I send it to you in this gossip network. So then a direct connection is established between these two nodes. So a stream. So that node sends that block like one by one, and then it replies, I have received it, until that stream has ended. So we can send data first and verify later, and this is called optimistic synchronization. So and that means that if we use this, we can. So optimistic synchronization means that we're optimistically thinking that the data is fine, and then we verify, and we can do so in less than a minute. So we're reducing the bandwidth. We don't have to wait for the network while the data is moving around, etc., etc. So the node will just take all the blocks and say, hey, I already have block 5. I don't need it again. We'll trust it's right, and then verify it. So here we can see like the Chicago node getting data from a node in Michigan. So 2 nodes where we're testing that stream of sending the delta difference of blocks and then verifying its correctness. Yeah. super for those who think that's interesting. But now let's look at some tests for fun. So as we see here, yeah. So what this was we have a sync node, verifier, and listener. So each node is communicating with every other node in the network, and that's pretty cool, because then we can see that this node here is, so these numbers is the local height. So that's how many blocks my node has synced. The block height for the network, so the network's max, the latest number of blocks. And then you have the numbers of blocks this other peer have synced. So here you can see like the total block height for the network was currently 104,000. My node has synced. I'm fully synced with all these nodes. And then the peer that I'm connected to here, I also get that information that he is fully synced. So here we can see a little bit lower that this other node only synced 21,900, whereas I have all the other ones. So now we can establish like nodes connecting with each other, and we can have like data insight as to how synced they are. So what nodes do, they're sending, they're forwarding, and they're receiving blocks using this liberal peer-to-peer, lib peer-to-peer, and quick for as a messaging. And then we can also see other data like the latency to peers my node is connected to. So between this node and my node, there's 92 milliseconds. Okay, and this is something like if you have milliseconds. I talked about this last time, but I want to talk about it again because I think it's so cool. Like how fast is really 100 milliseconds? Like it's pretty damn fast. So like I showed you last time, if you have two nodes, Sydney and New York, like how fast it traveled 100 milliseconds. So we can take the distance and divide it by the time, and we can see that it's like 53% of the speed of light. And the way it works is, so it works with this fiber optic cables that are, this is showcasing how they look on underwater, but they go with fiber optic cables on land as well. This is another thing like I never really thought about, but Jack knows like insanely much about how this works. So what it does, and I'm telling this just because it's so interesting, like you have from your computer, you have digital data, so like ones and zeros, and it converts this to light traveling in this fiber optic cables in portions of like 500 kilometers, because you have to have some nodes here and there. So it converts them from digital to light to digital again to light at these checkpoints until it arrives at the destination to be interpreted. So that's pretty cool. And now people say also, like, why nerd out about being so fast? Because you don't need to be that fast, like when we're trying to optimize. But here's the thing, like, I think we should strive to be as fast as humanly possible, if you can say that. Because number one, like, we future-proof it. Number two, if we can be fast with confirmations, we can also be fast with finality. So Solana has 400 milliseconds for confirmations, but they have 10 to 20 seconds for finality, which is ages. So not compared to Bitcoin, but still, it could be improved. So that's a very long time. So to push the boundaries first is ideal, because then we can use that later for faster finality within seconds instead. And for the third reason is for it opens up for many more use cases. So we can be like NASDAQ fast. So if we optimize for speed first, then we can optimize for validations in the next step. So yeah, just to because it's cool, because I really never really thought about this stuff before. But anyway, so some other things. yeah, I want to show this also, but I need to switch. I need to switch windows. Uh, yeah, yeah. I saw this. Tomo, he really hit it. It was funny. Best the meme of the day. uh, yeah, yeah, yeah. So here, we can see. Let's see if I can scale it up. Yeah, yeah. So here we can see the nodes in the network right now. So what's pretty cool with this, like, we, if we refresh the page, so what we here is node first, and then the block ID it's synced with, transaction hash, and etc. But if I refresh the page, which is super cool, I just refresh it and refresh it and refresh it. You can see how fast these nodes sync the latest blocks. So it goes incredibly fast, which is pretty cool. So what this is so what we can see is how fast the nodes in the network are getting the latest blocks. And what this is actually an early version for transaction validation and block proposal. So this data is getting injected in the peer-to-peer network. So the goal is for every node to have a state of the latest set of transactions and valid blocks. So this ensures that voting can happen. I will talk about that a bit later. And also here, if we go to the infamous Zen.pub, we can see, which is also super cool, like all the nodes. Now, probably most use VPN, but it's still pretty cool to see like the distribution of participants in the network that we have right now already. So 200 nodes spread out. Like, let's find the Profeta is in the house. Let's find Profeta. So here's here's Profeta in Amsterdam. So it's pretty cool. He's in this red light district. Don't ask who I know that, by the way. But anyway, so yeah, it's just pretty cool to see all the different nodes all across. What else? Let me show you some other stuff. Joe Blau. Joe Blau is coming over. I'll come too. Okay, I'll come too. No distribution. Yeah. So what you see is distribution of nodes or coordinators running code to report verifications of transactions. Nodes are rotated, removed, and added to the list. Each node proposes a set of transactions loaded into blocks. Yada yada yada. This is also like super nerdy stuff, but here's my server, one I rented on Latitude from Sao Paulo, connected to another peer server using this port and quick protocol using UDP. Here you can see the length in bytes. So the length is in bytes. So what is it sending? It's sending blocks here up at the end. You see it's 14,390. So that's the length. So that's the blocks. So it receives the blocks and it pushes it to other peers in the gossip protocol. And when everyone has these blocks, there's no reason to send that anymore. So I can have a fully synced chain, but I might be helping another node getting things through. Then I'm a rebroadcaster. So it pushes the state so everyone gets synced. So someone so Crypto Profeta in Red Light, he's sitting there. He's not fully synced because he was busy. Then he's asking for blocks that I have, and we're using this peer-to-peer communication to do this. So here's Jack and I talking and syncing blocks to each other, and many blocks are this size at its current state. And here's like if you unpack that data, you see like this is what we're talking about. but all I see is a blonde brunette and a redhead. That meme is so good. Here's also like the data exchange. You can see like between two nodes. You can use this like if you're connected with two nodes just to see like this is how much data my nodes my node is receiving and sending to your nodes. So we look at things like that, of course, as well. Steve, I'm in Netherlands too, but showing up in another country. The VPN. Yes, exactly. Good to see you, Steve. Yeah. And this is also something I wanted to talk about, like the network connection, because here I was using I was syncing with an internet connection, which was very slow. So then the syncing of the blocks became very very slow, and this is the same. So this is the same with a fast internet connection in the same time. How when I switched to and because I was at a place with a very bad interconnection, but then I just rented a server online instead and synced, and then it synced the blocks much faster. And I mentioned this because if we want very fast confirmations, having a fast internet connection is going to be like one of the criteria in order to be a coordinator. It's not really something you can do about because they need to sync very, very fast. And this is just an example how to show you, like, it's very hard to be a coordinator and you want to have a network which produces very, very, very fast confirmations later on finality if you have a bad internet connection. So that's very important. This was interesting because when we shut down the master node, which was pretty cool, then we could see, like I got this feeling that because there was one node that everyone was syncing to, but then when you shut this down, it was super cool because then you could see that the peers in the network who were syncing were like the network was still working. They were still syncing with each other. So it was like a feeling of like, wow, this is live now. This is super cool that it works. That's how I felt. Okay. This I saved the best for last, ladies and ladies, because this test was one Jack created to showcase the speed of the network, and this is pretty exciting stuff because he's optimizing this network like mad right now. So what this it includes a full cycle of confirmation. So it simulates full testing in a live environment. It's not a synthetic lab, all the way from initiation to writing to disk. So what it does, it sends thousands of transactions from your browser to a server. The server does computation and puts everything into a database. It adjusts the balance, it manipulates the state, and then it reports back as well. And all of that in under 1 millisecond, which is insanely fast. So let me just show you. Oh yeah, we are zinking. That's the funniest commercial of all time. What are you thinking about? Let me just show you this test and break it down, because this we have to do this test, and this is going to give you confidence that we can be faster than Solana for sure. So let's see. Okay, let's now I refresh the page. Okay, so we update the page. What it does, you can see how it generates these addresses. So these addresses are they have their individual private keys. So think of it as like 20 different wallets. So what I'll do is I will hit a key. There's been different versions of this test, but this is my favorite. So you hit a key, and then it generates all of these transactions from these wallets. So let's do it right now. Bam, 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 bam. Look at the speed right here. Wow. So what happened here? We have a multitude of colors. So the colors represents like how fast this transaction was generated. So purple, dark purple means it was super fast. Green is a bit slower, and let's see if we have some red ones. We don't. So yeah, nice. It's always nice to have fast when you do a tutorial. Now the thing is, check these numbers. So we're going to dive into them right now. Like TPS, transactions per second. We have transaction latency in microseconds. We're talking microseconds here. And then we have a total of 5,000 transactions. So what really happened here? Like what's going on? What did we just do? It was fun to click the button, but first there was a test. Do I have it? Yeah, this one where you're supposed to just like hit the keyboard as fast as possible. Oh, and then that was a funnier test. And then like how many you could see how many. But the hack to this was just to hold down a key, and it would it would generate the same. But anyway, let's unpack what exactly happened here. So remember this. Something happened with some kind of addresses. We generated TPS. We had some kind of latency. What the hell that means? And it involved 5,000 transactions. Okay, what's going on? What's the fuss about? I'm gonna fuss it up for you right now. So let's feel fussy. So here we go. So we have 20 different wallets, 250 transactions in each, and it was a total of 5,000 total transactions. So when you hit the key, the what happened was that each wallet generated 250 transactions each. Okay, the balance is 0, but they just generated a transaction. So total 20 times 250 is 5,000. So what it did is the server processed all this data in 207 microseconds, and this is per transaction on average. So first of all, let's just unpack like what is a microsecond. So you have 1 second. It's like 1, 1, 1. You have 1,000 microseconds within that, and then if you go deeper into the 11s, you have 1,000,000 microseconds within. So 1,000,000, 1,000,000, 1,000,000. It's insanely fast. It's so fast that you can't even like comprehend it. That's how fast it is. But anyway, so if you take 1,000,000 microseconds, which is 1 second, and you divide it by the microseconds it took to process one transaction on average, you get a TPS of 4,800, and that's for one core, single thread, no multiplexing whatsoever. Now, that is like a live test. It's not synthetic. That is like super cool. So if we then have a machine which has 48 cores that Solana has, that's 192 transactions per second, which is pretty cool. And this is just like, what's insane with this? This is just like Jack. First of all, he learned Go in a weekend. He didn't know it before, and then he got it to work like this, which is pretty cool. But let's unpack in detail further on what exactly happened here, so you guys follow the whole process. So yeah, so let's look at what happened. You hit a key in the client. It generated private keys for 20 addresses. It signed 250 transfer transaction each for every of these 20 addresses. So it then submitted. It just sent out a total of, from your client, 5,000 transactions. Okay, so it's 5,000 transactions relating to 20 different addresses, okay, with 250 each, and each one of them also has like data of whatever balance. So imagine this comes to an RPC. In our case, it's going to be a coordinator. What this does, which is absolutely nuts, it receives the data with the transaction balances in instructions. It then verifies all those signed transactions using cryptography. We'll talk about later. It checks and updates the balance. So it updates the ledger in the local DB. So every node has its own version of the state, right? It then stores this data in something called RocksDB. It's a database. Solana also uses it. It's very fast. You can do millions of queries. It uses memory very well, etc. But it stores this data. It then assembles a block with it because that's what the coordinators do, right? It creates a block proposal, and it then pushes this block to connected peers in the network. And then it also reports back to the client. So to where you are. So this is a full cycle of confirmations. This is what happens. This is a job that needs to be done, and all of this under 1 millisecond. Okay, so Solana does. They have a block time, so 400 milliseconds. So do you get it? And this is asynchronous, which I'm going to talk about next as well. This process. So it's insanely fast. Now, like, just imagine for like chains, it's really like ledgers. It's like bookkeeping. It's like accountant. Now, imagine you have your real life accountant, right? That does all of this work. It's insane. Like you come to your accountant and say like, hey, I know it's closing of the books and it's March, but hey, can you take all of this accounting I have? I need to also, you need to log into the bank and prove that you need a bank statement to really prove that it's my transactions. You need to check all the bookkeeping, and you need to store the data somehow, and you need to create a report with it. And if you could do that in like under a millisecond, that would be great. But this is like what we're doing. It's so insane if you think about it, like the efficiency of the technology that we are creating. It's so insane if you're relating it to the real world, to the normal world. Like to do all of this accounting or bookkeeping, it's so cool what we can do with this technology. Like we haven't even begun to even comprehend, to understand what we can do with cryptography and with blockchains. That's going to solve like 1 billion use cases in the real world. So I guess we can say we're pretty early still. So you know, all the KPMGs and the Price Waterhouse and the Deloittes and the PwCs, they have no idea. They have no idea. But anyway, so latency, what is that? Like that is a receipt. Okay, so that's how quickly your node can generate a receipt, and that's per transaction on average. So this is from generation of private keys to storage and broadcasting, but it's only this part. Okay, let's be clear and honest with that, because this is the user input, so we can't control that. Okay, how fast you're gonna create this transaction, and you're probably not that fast to create that many transactions, but the whole network is, right? So, and a node needs to be able to process that. So even though you did this as a single user from a client, it simulates like let's pretend that the whole network is doing this, and it doesn't also include like the network speed. So the time from it takes from you as a user to produce those transactions, and that for that to go to the server, because we can't control that as well. But this is calculated from like when you receive the data from your server. So yeah. Let me know if you can hear me all right, if you're still following the stuff. Let's see. ProDank sharing leads to about 1 megabytes per 12-second slots, or 2.5 terabyte per year, which is much more than Ethereum needs today. The ETH solution is to forget history. How will XenBLOCKs solve storage concerns? That sounds like a Jack problem. It's cool with Joseph. He knows a lot about storage too. How it will store. Yeah, Joseph. That's for you to solve. I really don't know anything about databases, so I can't. Nice, thanks. Damien, how you doing, buddy? Rocksteve yields the Whitney Houston data. Right. So, but with a really fast CPU that's like pretty affordable, like 1 year old, we can also get like this down to 72 microseconds, which is like 3 times faster. So that would generate like 500,000 TPS if you used all cores. So this is like real data. This is not a synthetic lab test. It's just what like the data is telling us. And another protocol we're using for this is WebSockets. So I told you about lib peer-to-peers. You know everything about that now. But it's kind of like lib peer-to-peer, but it's different. It's been designed for browser real-time communication. So you don't have to establish a connection every time. You can maintain a connection between two nodes. So voice over IP and streaming is using WebSockets. So you can distribute a lot of data to all the coordinator nodes. Okay, we can talk about that later, but coordinator nodes are very important because they handle the confirmations from the transactions and very fast. So lib peer-to-peer we use for efficient distribution of blocks to all miners. Okay. And all full nodes in the network. And WebSockets we can use for real-time communication among coordinators, so they can have a real-time stream of informations. Because the thing how it works is like with an RPC server. Like if you are interacting with the chain from your client, it gets to one node, and so it comes to that one first, and then this node needs to gossip this data as quickly as possible to all the other peers or all the other coordinators in that network, so they also have a chance to process that data. So sharing is data caring. But now the question is, okay, this was done from like one client to one RPC. So can we give all 5,000 transactions to other nodes at the same time? And this is where WebSockets come in. And the results for that are good, but it just takes a little bit extra time to send, but not substantial. So yeah, the question is, how fast can the other nodes get this data? Because that's substantial to know the transactions time. Because yeah, if it takes one node 200 microseconds to process that data, I mean, 200 microseconds, it's so little, it's insane. So Solana has 400 milliseconds. So in 1 second they can process 2.5 blocks, but we can do like the validation or that processing in 200 microseconds. So the next step, that's my point, is to figure out how fast can we get this data with WebSockets to be transported to the other peers, to the other coordinators. What else? So what this means basically is that you have to verify, you have to decrypt, you have to update the database, you have to assemble a block, you have to push the block. And the point of all of this is that we can do this with our model asynchronously. So the miners, they don't have to wait for the chain. They can spend their time to assemble the chain. And they do so with 1 block per second. So coordinators, they process all the transactions, they package into 2 blocks, and they give it to miners for assembly and block creation. And this is the model that we have with delegated proof of consensus, which will make it much faster than Solana and also Avalanche. So we can be like 1,000 times faster than Solana if we follow that model. And this is what we want to prove with this. So they have 400 milliseconds per slot, right? But that's for confirmations. That's not confirmed finality, because votes come later. Okay, finality for Solana is 20 seconds, and this is why I like degened all the all the way with you to like really going into the bare metal thought of like how can we optimize the system to the bone. So Bitcoin does 6 confirmations. That's when it's considered to be like a final. So that's 6 confirmations. That's 60 minutes because each block is 10 minutes on average. And as you know, like watching mempool.space, it's like watching paint dry. It's so slow. It's like even worse. But we can do verifications in seconds because the miners are producing the hashes. So we can use them to verify. So if they do 6 verifications, that's like deep confirmations. There's like no way that transactions are reverted. It's like too many peers have confirmed its legitimacy too fast. So immutability can be confirmed. Like that's finality, like in maybe even like a second. Let's see. Let's see about that. Broadcasting can happen in like half a second or even less to other nodes. Yeah. So here, okay. Now, what this test reveals, like, expand your mind, because it gives a user ability to process transactions at the speed of light almost. Okay. So, you know, if you think about it, Jack said this super funny analogy, like it should be as fast to transact as sniping someone with a HS in CS. You know, if you know, a headshot, you know, like a real-time experience. So imagine like market orders or mining NFTs that quick, which we should play with very soon, just to test the performance of this. So Anatoly, founder of Solana, respect very much, a super smart guy. Now his vision for Solana is to make it like the new settlement layer, the new NASDAQ. But their consensus model is not optimal, I think, or we think. And I will talk about that in detail, because his ideology is even very interesting, though, because it's like the cheapest chains we have, they're not even cheap enough. If we're talking about transaction cost now, the transaction cost should be close to 0. Because like anything above bandwidth is really a tax on the consumer. So you're taxing the whole crypto ecosystem. So you're reducing the ability for people to come in to the ecosystem, which is a very interesting thought. Like it does have a point in that, undoubtedly. It's something to think about. And then the question is like, okay, how do we then make sure we're not spamming the network? Like if it doesn't cost anything. But that opens up then to the next thing, which is like segregation of fees. You can have one channel for normal transactions, one for NFTs, one for whatever else. So we save that for another stream. But as I will talk about next, the proposers, they propose the block, the coordinators. The miners build the chain. And this is an asynchronous relationship. So the miners don't have to wait for the coordinators. And since we're proposing a model with no forking, so there's no extra overhead of any processing. We don't do forking. So that means we follow the avalanche style of probabilistic consensus. So these are some of the things I will talk about. Just to finish off, this is Jack doing the same test from a Starbucks Wi-Fi with the high amount of BPS. You know what BPS is now. So let's see. I have XenBLOCKs in Palestine, but it's in the data maybe. I'm not sure. We can watch if someone has a VPN in Palestine, though. For faster speeds, would you need more data storage than other networks, or does XenBLOCKs code allow miners to create greater efficiency in the network processing speed? Would you need more data storage? So yeah, that whole thing is a whole segment that I personally don't know so much thing about. That's a Jack question. We should do a stream with Jack and all of this very soon. So this was sort of like the pre-com, and then he come in and like slam dunk this guy Pippin I just did. So I because my strong suit is really not storage questions at all. But anyway, I'm good at moving on, so we're going to do that. So that's a good question. It's a good question. Anyway, I think we can be very fast. Let's just say that. But now let's look on the peer-to-peer on consensus. So now we move away from the data availability layer and move in more to consensus. So we talk about peer-to-peer propagation and broadcasting to probabilistic consensus. I have to say that. Before we do that, let's just do a quick recap of what we talked about last time on last stream. So the question is really like, how do we leverage the whole peer-to-peer network now using Quick to transfer data and lib peer-to-peer and WebSockets to control the flow of data to find consensus in whatever it is we want to find consensus about. So this is from the last stream. So we're adopting the concept of delegated proof of consensus. So we have two layers. We have the proof of stake layer for confirmations and the proof of work layer for finality. And the proof of stake layer, which consists of coordinators taking the transactions, producing block proposals, the proof of work layer, do validity checks on these blocks, and then vote for their accuracy, and then majority wins, and the block is accepted. So listen, guys, I do a million different models, okay? Because I like it's easier for me to understand things when I have a visual representation of something. But I do a lot of different models, and they basically all sometimes say the same thing. But the way I think about it is, it's like looking at an object, okay? So you see the same object, and it's the same object, and I'm describing a model to it, but I'm seeing it from different angles. So it's the same thing I'm describing, but with each new angle, there's some kind of new information. And we do like a million of these different models until we find like the 10 perfect models to represent everything we're doing. But that just so you're not confused. And what, by the way, this is a super cool watch. Like, see how cool it is. And I saved the price tag. It cost like $7. That was so cool. It looks like it could be like RH level watch, but $7. I should have it here in the background and have it rotate. I need to figure out how to do that. That would be so fun. Anyway, where were we? So yeah. Now, how do we combine these models? But my point is, I'm not afraid to make a million different models. It's your problem to process all of them. So what happens here? So the coordinators, we have a set of coordinators. We say 21, but it can really be however many fills the criteria. It's just when we say 21, it's just for it's easier to make examples with it. So what they do is they look into the network, they receive all the transactions, they run verification, which I talked in last stream, using Ethereum method of nonce to check for double spend, etc. So for instance, you have 10 transactions, it creates 10 hashes, and then from that you Merkleize it into you do Merkle root into one hash. So they publish that hash into the entire peer-to-peer network. The mining nodes in the proof of work layer then receive these hashes, and then they vote for them. So majority wins, minority hashes are discarded, and that's how they find consensus. So another way to see the exact same thing is like you have the coordinators, a majority of them run good hardware. they package a bunch of transactions into a block. A majority hash should be the same. Miners look at the hashes, and out of 100 block proposers, 97 of them produce the same hash. So they look at the block and verify its contents, they vote on it, and after a threshold vote, 3 to 5 seconds, that block is added to the chain. Yeah, so and yes, and you remember we talked about this. It's like an early version for transaction validation and block proposal. So the data we have is getting injected into the peer-to-peer network, and the goal is for every node to have a state of the latest set of transactions and valid blocks, so that voting can be possible. Okay, so you need, as a miner, you are a miner, and you need that data so you can have an ability to vote. That's basically all I want to say about that. An alternative, like if you go to another layer of now we said like the hashes are being propagated, and this is a program that Jack made, which is also super simple. So this is a program that looks for blocks instead. So if they see the same block, it's then it's consensus, and that's it. So you can run this with any node. So you have a view with peer-to-peer, what everyone here is reporting. So you can see like what the peer are reporting, the peer ID, and that they're reporting that block. So everyone shares the block info. It's the same. It means that everyone has done the job. So they're not sharing the hashes. It's broadcasting with this RPC node. So this is another way to have consensus, and it also works on this subscriber broadcasting model with live peer-to-peer. This is pretty cool because it's just a simple algorithm. It's one line of code in Python. So it's a very simplified version of Avalanche that use probabilistic consensus, which means that if you look, and that's very cool what they did with like the Avalanche crew is pretty smart, because it means that if you look for 100% consensus, that makes everything very slow. But if you reduce the demand to only 99.99999, it's much easier. So you don't have to have a lot of noise like Solana. Solana uses hard consensus instead. But what's important is the consensus. But this is just to show you, like whatever the nodes need to find consensus on is to be decided. But the important part is that there is consensus. So it basically means that just with a few iterations, you never really get to 100%, but you can get to 99.999%. So an insanely high level of probability, with knowing that it is correct. So that's very cool. Now let's continue talking about a little bit with some transactional properties, and the it's gonna take some water. First you get the power, then you get the money, then you get the models. Exactly. I reverse that. I get the models, then I get the money, and then you get the power. What he said. So it's lucky when he said do a million different models. I wish, though. I wish. Jesus. God damn it. I'm spending way too much time with you guys. I could be out there Copacabana in fucking enjoying myself, but I'm stuck here with you and these fucking models. But it's kind of okay too. We're still in bear, guys. We're still in bear. So right. So let's look at it. Like, let's just break down apart, because if we're gonna optimize shit, we need to like break down like what is really a transaction as well. coming into the network. We need to see their size. Like, how do we even begin to optimize though? So we need to see the size of transaction, the network capacity, the broadcasting speed, how fast they can be transacted, and what size that data package that needs to be propagated. Like we go very deep in one direction and see what it's capable, but then we need to really think about like how many transactions will there be, and what is the size of those transactions, so we find a good mix of everything. So let's just break down some shit to that, and we can start looking at a transaction size. So first we need to know, like in the base case, like how big is usually a transaction, what's included in transaction, we need to know first of all. So this is a simple Ethereum transaction. So it's nonce, it's up to 32 bytes. It's really like just 1 byte. Same with gas price, gas limit. You have the to address, so the address you're sending to, the value, so the amount you're sending, the data, which can be like from 0 to unlimited. In our case, the balance was 0, so there was not really much data there. The VRS. So what does that mean? That is the signature. So for like the from address, so we have the to address specified here. The from address is part of the signature. So you use your private key to send the transaction. And once you have the signature, everyone can verify that it belongs to you. So because otherwise I can just pretend to be you and you see my Ethereum address as the from. So the transaction needs to be signed with the private key. We're using encryption. So it's basically the same as like each hash in a block is a solution with a key. So it's kind of signed, and each hash is signed with a hash. So you can verify that it belongs to you. So it's kind of like a signature as well. So in total, like minimum for Ethereum, it's like bare minimum, it's like 80 bytes. But you're most likely than not to transmit something like in your transaction, unless you're spamming Solana. So a transaction on Ethereum, you say, is like 120 bytes. But let's round it up to 200 bytes, just for sake of argument. The other thing we need to think about is encryption. Okay. Because different networks use different encryption methods. And what's important to think about here is some of the aspects is encryption in terms of speed, in terms of security, but also compatibility. So signatures, they need to be encrypted. So when you send a transaction, you have to sign it and you have to compare the transaction with the data that you are sending. So various networks use different algorithms to encrypt the signature. Bitcoin uses SHA-256, Solana uses 25519, Ethereum uses Ketchup, Ketchup 256, which is some kind of version of SHA-3 initially. I'm not really sure exactly like what the deal is between Ketchup and Ketchak and SHA-3. So the thing is, though, that different hashing algorithms has different properties. To my knowledge, SHA-256 is 50% faster than Ketchup, and ED25519, which Solana is using, is many times more faster than Ethereum. So to generate a signature with Ethereum, it's 10 times slower than Solana. To verify a signature, it's 30 times slower. So there's a lot like better, faster cryptography that are not Ethereum. But the thing is, if we want Ethereum compatible, if we want to be Ethereum compatible and Ethereum wallet support, we need Ethereum cryptography. And there's obvious benefits to being plugged into that as well. But it's something to consider, because we can create our own wallet as well as Solana, but then you have to convince everyone to start using it. And we know this, from going to all of these chains, like you're not really going to do it. It becomes a hurdle. Like we know this better than anyone. 12 different chains, all of them have their own wallet, and you're sort of like, it's like, you know, welcome to our chain, and please use our base wallet. It's like, yeah, I don't like MetaMask like at all. That's the problem. There's much better wallets, to be honest. It takes like but the question, it takes a lot to divert from it, to be honest. I think if they're like really serious about implementing some kind of KYC for using MetaMask, I think though that's what it will take for people to be like, oh no, that's it, no more. So in a way, it would be kind of interesting dynamic if they would do so, because we would for sure be like, no way, we're gonna use KYC to use like a wallet. But it's kind of worrying what's happening with the state as well, especially in Europe. Like they're pretty dystopian in their argumentation for the European Union has a lot of power, and each country is giving them a lot power as well, without realizing what's at stake. That's really how I feel like. But that's something that's another topic. But the reason, for instance, Solana can't use MetaMask is because they're using other cryptography. So we can actually switch to our own cryptography as well. That's even faster, because I can use both Ethereum encryption and something faster like Solana. But Jack is digging into this deep as well. And so let's see what comes out of it. But the important thing is to realize that if we're going for speed, we have to make sure that the signature encryption algorithm won't be a limiting factor. And the various factors that come into play, like speed, security, compatibility, and privacy. Self-custody, of course, as well, but that's given. Let's just mention briefly on broadcasting speed, just to think about in the terms of like upper limits of what's even possible. So the upper limit is like how fast a single server can broadcast, and it's our case, it's the RPC node. So the theoretical limit that is reasonable is 1 gigabytes per second. Let's assume that. So for 200 bytes transaction, that would be 5 million transactions per second. That's the theoretical upper limit. But without looking at like the transaction at all, just receiving them. But then you have to like work with them, you have to process them, you have to run cryptography, etc., etc. So what we can see on a really busy server is if you're running 2 CPUs with 24 cores, each is like 150 transactions per second per server. So assuming that the network can send a lot and not limit in any way, the CPU will limit you to 150,000 transactions per server, and you use the CPU to process the transactions. But don't take these numbers like to the bone. It's just to mention that there are different areas that we need to look deeper into. Just like show that there's something with limitations of broadcasting speed as well. But then when we have all of that, then we can look at like a data package. So we can assemble a data package and see what's realistic, because we know the average transaction size, the cryptographic signature, and the network limitations. So example, if we have 5,000 transactions per second from the network, one transaction is 200 bytes. A transaction on Ethereum is 120 bytes, say 200 bytes. That would give 1 megabyte of data package per second, which we easily can do. That wouldn't be a lot. So 1 megabyte per second is not a lot. So therefore, we can then make the conclusion that we can give it to all nodes simultaneously. You see how it connects? And then we can have a system where the coordinators are making block proposal in parallel with fast finality by the proof of work miners. So that's how to go about thinking about this stuff. But that's just like a few features and restraints. So this is just like the warm up for going deeper into that. Now let's go into block production. More models for the people. So now I'm broadcast. Now I have by default it like StreamYard wants to stream at like 720, but now it's 1080. So I think let me know, is this resolution, can you see this model like good on your various screens? Like if you're watching this from a cell phone, it's probably too low. When I make models like this, I should really think about more compressing them, because I want to like show the whole model and not zoom into different parts. But anyway, the important thing with this is that now when we know like how much transactions comes in from the network, we can put all of this that we talked about into the context. So transactions come in to this peer-to-peer broadcasting layer, and it's super also annoying that there's a delay with StreamYard from the in the comments. But anyway, we know transactions coming in from the network. They go to this peer-to-peer broadcasting layer, and it transmits this data package of 1 megabyte in our example per second to the coordinator nodes. Okay. So we have this coordinator 1 to up to n. On this thing with the coordinators, like the number of coordinators will depend on the difficulty to be one and the incentive to be one, really. So what you want is for the barrier to be low for decentralization's sake. So you want them to be very powerful. So you want them to have like very good hardware, very good interconnection, and that will be like a requirement for sure, so they can process fast. Because as we've seen, like with multiplex and multiple cores, it gives you multiplex gives you great TPS. But this sort of contradicts like the fact that you want the barrier to be low as well for decentralization's sake. So there's two forces that are in contradiction here that need some sort of balance. So Solana validators is definitely like a ceiling referring to hardware requirements. Ethereum validators is definitely a ceiling when it comes to stake amount, with 32 ETH. So it's important to like optimize everything else first, and then we can see what is what is the requirement for them. Anyway, they receive this data from the network. Okay, they make these block proposals. Okay, so they propose blocks from these transactions, and it's parallel block proposing production. It should really be. So they're proposing these blocks. It then goes to the decentralized mining layer, which is all the miners, which are producing 1 blocks per second or 60 blocks per minute. These miners, they vote on the correctness of the proposed blocks. So they vote and they say, this block got this many votes, correctness from us, and so on and so forth. So what we can see here is like coordinator number 1. This is very simplified, but he voted. He got the votes from the miners. Like 5,000 out of 5,000 transaction were okay. They were super good. So he will then get a reward, and that's his incentive to calculate correct. Coordinator number 2, he also did it correct, but he was not active coordinator at the time for this epoch, so he doesn't get a reward in that case. Coordinator number n, he fucked up. He did something else. He got everything wrong here. He didn't even get the total. So what happens with him? He will be slashed or removed as a coordinator, or some other kind of suitable, suitable punishment. Could be spanking as well. Unless he likes spanking, then that should be here on the reward side. Oh yeah. Anyway, so anyway, if he fucks up, he will be removed as being a coordinator. That's what I tried to say. And once you have enough, the threshold vote, it will be accepted in the block and accepted in the state. So that's sort of like and the coordinators nodes need to stake some amount as well. So there's going to be some level of need to run good hardware, need to have good condition, internet connection, and need to stake some amount, etc. So we can slash them as well if we want to. But that's sort of like very simplified how this whole model works. There's no forking here. Okay, there's no forking needed. This is a key point that I will bring up later. But that's very cool. Now, I mentioned here that these coordinators, they are rotating. Okay, so you have a pool of coordinators and they're rotating, and one is elected by the proof of work miners as the active coordinator at the moment. At some time interval. So it can sort of look like this. Here we see sort of time going from up and down. Here we see time going from down and up. But it's because I envisioned it as being like tractors that are going on a field for no reason at all. But anyway, so what you can see here is that you have this coordinator here. So first you have an active coordinator queue, let's say. So this green ones is those who have been active coordinator one by one and produced these block proposals and done so in a good way. And here we can see number 2, 4, and 12. They're coming up next. Okay, so we have the previous active coordinator, number 1, and then we have the upcoming coordinator here that's going to produce next. So what has happened here is that they all propose, you can call it like lightweight block proposals, okay, because it's not really like an immutable block yet. They're proposing a block to the chain. So they're all doing this in parallel, right? So they're all doing it they're doing the same work. Number 2 here, he was active coordinators. So, and he did a good job. He was a good boy. That set of blocks in that epoch, in that slot, then became voted in by the proof of work miners as a chain. Then it was time for number 21. He did the same thing, and then number 1, etc. So the proof of work validators, they vote on the accuracy of the block finalization and settlement, right? So that's all frank dandy. But what then happens if there's something it doesn't go right? Because if it's like, and you can call it like fork management by votes instead. So there's no forking. So in this case, coordinator number 1, he fucked up real bad. He did 2 blocks right. He was active coordinator, but then he fucked up real bad on the rest of the blocks. So what's going to happen then? The proof of work miners, they are simply going to vote for the next one or the other one, or through some kind of mechanism for whoever of the other 2 to n coordinators got it right, and that's going to be instead chosen as the state. So it's kind of like sequential block production here, but the block proposing is in parallel. Okay, so that's what makes us scale. Like that's the gist of it. Like if you connect all the dots that I've been talking to you by up until now, that's like the gist of it. This is like scaling, because you're not at the end of the day, you're producing a chain that is like sequential, but the process to get there is not sequential, so to speak. So if we just unwrap that, so like what happens when active coordinator gets it wrong? The number 1 is active. He gets 2 blocks right, but malfunctions on 3. And what simply happens is that the miners will choose to go with 2 instead, which has a better accuracy. So there's no forking needed. And this is a major difference from Solana, which I will talk about later on. So if the active coordinator is well functioning, their hash will be wrong and they will be removed from the set and or get spanked. So if the actor, but if the majority of the others that are in the queue to become active, supposed to have the same hashes to match against each other, the network will see that. And once we settle on the right hash, then we will remove the active coordinator that's malfunctioning, promote the next one in line to be active, take the hash of the data and vote for inclusion of that block to the chain, to the blockchain. So once it's deemed to be inclusive in the peer-to-peer protocol, it will start to push this to the state, the blockchain DB. And blockchain DB is currently running Python and sync node. So we have a version of sync node that will be faster because you can grab all the blocks, not directly from this central node that we have in the beginning days, but from the network itself, which is decentralization, of course. And this is what we want to take it to, from the peers that are closest to you. And the coolest thing about this is that the block hashes is produced in parallel and that there is consensus. So if anybody loses transactions, then we can quickly discard them and just choose the ones that are good. So we just package the block, send it out to the network, and then append it to the state, and it becomes immutable. So that's like, in simple terms, how we handle like malfunctioning of active coordinators, or as Solana calls them, leaders. So in a way, that's it doesn't need forking in the chain. So to summarize that from like a participation flowchart. So I have this and one more thing to cover. It's been a marathon. Get some question. Mid-Stardust, how often can be the coordinator? There needs to be a coordinator schedule that does make sense. So in Solana, I will show Solana's case next, but there needs to be some kind of schedule that does make sense, but that's something we can choose, and that's something we iterate. We haven't really discussed like those details yet, but it can be either like on a second or 5 second or like a minute or whatever will make sense. But like as long as you're filling up the requirements of what does make sense, I will talk about this now, actually. So think of it from your perspective now, okay? Think about you. We need to think about you here. So you start as a miner, okay? This is the entry point of participating in the system. And you know how to be a miner. You know how to be a hash head. You know what it takes to be a hash head. So you start as a miner, you find the hashes, okay? You stake, you fill the requirements. So you stake XenM, you have good network connection, etc., etc. If you do all of that, you can be elected to be proof of stake in the proof of stake coordinator pool, or whatever we want to call it, like the swamp. We should have a cool name for this, like the swamp, the coordinator swamp, or something. So. And you are elected by the miners. Like the miners, it's this great analogy Jack has. The miners are like the people, and the coordinators, they're like the Senate. They get voted in to run, but they only have like limited power to do like very specific tasks and follow strict rules for doing so. And they immediately get moved out if they try to do something bad. Like we're gonna spank them. So they get chosen into this proof of stake coordinator pool. The miners then choose, also with the schedule, active coordinator through the schedule. And this is what you ask, like how many times, etc. No idea. The active coordinators propose blocks, okay? The proof of the other are doing it as well, the other coordinators. So they are doing this in parallel. Now, if it gets voted by the miner, it gets an immutable block after a threshold votes. So it gets into the chain. Now, if you look at it from another perspective, let's say, so this is like the coordinator route, okay, here to the left. Just to be extra clear. So this is like the coordinator route, and whoops. And this is the proof of work miner route right here. So what you need to do, you need to be a miner, you need to run sync node, you need to sync the chain, etc. So you need to have all of that data so you can make the votes, right? So as we talked about. And then you sort of become a validator. The term validator, we need to also decide with the terminology, because the coordinator is sort of validating the transactions, but the proof of work miners are validating the coordinator's work. But anyway, they validate the proposed blocks by vote. And if they vote wrong, their rewards are also slashed. Okay, so what happens is once this block is gone through like the whole assembly line, then you need incentive mechanisms to kick in. So the active coordinators, he can get like transactions free from the network, for instance, for that specific time that he was active coordinator. He needs some kind of incentive to be a good boy. The miner gets XNM. And this is also what I wanted to mention now, because this is something that we can discuss in the Telegram, what you guys think makes sense, because we have this schedule, right, of Xenium to be distributed, and it amounts to, like, since it's yearly halving, 310 million, so it's like 600 million in a year. Now, what we always said from the beginning was also that the miners need to be incentivized somehow. So we talked about then to give the miners like 25% extra blocks for every hash they find, for every XenBLOCK. You remember, like, if you find a block, you get you get here year one, you get 10 Xenium. So we said that, like, you can get 25% more if you also participate and in the decentralization, in the mining, in the peer-to-peer network to validate the coordinator's job. However, that sort of like increases the supply, which is also like feels psychologically bad. So what we also could do, which is probably a better solution, is to say that, hey, if you're a miner, you get 10 Xenium per block, but you also got to participate. You also got to do your shit, man, for what we're trying to do here. You also got to run sync node and be a proof of work miner. Now, the thing is, for the coordinators, they need like better hardware because they need to act very fast. But the proof of work miners, they can more or less take their time a little bit. They don't need to rush like that fast. They can take it like at least a half a second. So they don't need like to be insanely good hardware. So we're not like increasing the hurdles for decentralization participation that much, sacrificing decentralization. But my point is, instead, you get like we're reducing this. So instead of 10 Xenium for the first year, you'd get only 7.5. But if you participate in becoming also a proof of work voter, then you will get the 10. So it's sort of like, in that case, I mean, it's the same thing really, but it sort of reduces the supply also. I know that's something like that's the thing that's going to be most talked about after this whole stream, probably. Anyway, we're going to finish off by talking about Solana, like, because when we're proposing this, we're looking at a bunch of other different chains and models, like how they are really doing it. So it's pretty awesome that you stayed so long. So some of the problems we see that we think we solve with what I just presented to you. So fire dancers have got a lot of hype now, but it doesn't really solve these fundamental things that I'm going to point out in Solana, because in Solana validations occurs with proof of stake validators. And here's how validation works in Solana. So this is like the best case when everything works as it should. So you have a leader, which we call active coordinators. So here that leader is A. So you have all the validators here, A, B, C, D, E. And then you have so validator A, he then gets elected to produce blocks in slot 1, 2, 3, 4. So a slot is an opportunity to produce blocks, and the average target time for a slot is 400 milliseconds. So you have 4 slots, 1.6 seconds, right? 400 milliseconds times 4 is 1.6 seconds. The leaders, they're assigned in slots of 4. So every 1.6 seconds, there's a new leader assigned, a new validator. The gray dots, they represent the replay. So every validator and RPC node replays and executes every single block produced by every other
validator. So if they're not producing blocks, they're not sitting idle, they're verifying and validating blocks produced by others. But the thing is, that's in replay. We have parallel block proposing at the same time. So our coordinators do it simultaneously and get voted continuously by the miners. In Solana, validators sort of wait for the leaders. Now, but with this system, there's a lot of things that happen that the network has to deal with. So here we can see a situation where one validator skipped producing slots. So and you know, so that can be for whatever reason. Like there was a sale on some store or something. The internet connection was bad, or for whatever reason they didn't do their job. Okay, so they don't produce any blocks. So what happens here instead, that validator G, who's next in line, he picks up and builds block 9 to 10 instead. So he's skipping slots. And skipping slots is very common, and it's sort of expected in Solana network. It sort of works fine as well, to my knowledge. It's not really a big problem. But the thing is, it makes it have time delays. Okay. The next thing is that forks happen all the time. So here's a situation where validator C has a slow network. He has bad hardware, etc. So before validators C can produce blocks for slot 5, they first have to finish the replay and execute of slot 1 to 4. And if they are slow in doing that, they will stop producing slot 5 too late. So by the time they then produce and propagate block 5, the time will have passed so far, so it's now time for slot 9. So validator G here, he will start slot 9. He hasn't received the block 5 yet, but he will start from block 4 and build a block from build a fork from slot 4. Okay, so validator D, he then takes block 13, which is where he is assigned leader. Now, by this time, he sees that block 5 by validator C produced, even though delayed, but it's now produced. So now he can start a fork from slot 5. So he's skipping the block produced by validator G. Long story short, you now have a situation where there are two competing forks. So they need to resolve that, and they do. But the thing with this, it takes a lot of energy, and these forks can lead to delays. This is the reason why so much as 32 blocks is required for finality with Solana. That's why their settlement time is 10 to 20 seconds. So here's some other like forking events. You have here. Here's some other things like can happen in different scenarios. You should find this guy explained it very well. But he's not happy. You can see he's always like sad because there's so many forks happening all the time. So sad. Because here's a situation, but he's very good. I have to give him that. He was very good to explain this. But here's a situation where it led to a Solana crash because there was a situation with duplicate blocks. So there was a conflicting loop which led to a perpetual loop where neither could get a supermajority of these duplicate blocks. So duplicate blocks can also happen, which need to be resolved. And ultimately, whenever there is a fork, they end up working really, really hard to resolve that forks within the network. Because the reason to have this system is because they inherently have a sequential block production, like many others, like Ethereum and Bitcoin as well. But instead of 10-minute block times, they have 400 milliseconds, which is super fast in relation, right? So forking is inevitable, and there's a lot of forking going on, which needs to be resolved. So we think that our model with parallel block proposers, with coordinators who propose blocks in parallel, and then simply a super majority voting from the proof of work miners makes us so we don't need to have to deal with forks at all, or time delays, or duplicate blocks, and we can have faster finality as a result. So that's what we are trying to do with this system. It's as simple as that, really. Like, that's a question we have. Can we build a system which doesn't have this like overhead of work that Solana has? Another thing like to point out with their model of leader rotation is that, as they say here, you can read this on their docs, like at any given moment, a cluster expects only one validator to produce ledger entries. By having only one leader at a time, all validators are able to replay identical copies of the ledger. Yes, but this in itself is like bound to create a lot of mistakes, many inevitable forks, like unnecessary work, in our opinion. It's better to have like many do the same work right away and then vote, because with Solana, there's no consensus of leader work being correct if it breaks. So we can have consensus across a leader and its coordinator and proof of work miners. So Solana validators has to like talk to every other validator and resolve when a leader is malicious. So there's no backup without inevitable forks and delays. So that's like point number one. And then we have to talk about this, guys. So transactions per second, traffic, and transaction count. Okay. So Solana is reporting 4,508 transactions per second. Okay. So transactions per second is like, it's a key metric that everybody uses. And it's sort of like an important metric too, because it sort of shows like how it gives a glimpse of how the network can function. Like, and it's also like how it can how much it can handle. And it's also a comparable metric to it's like a metric for adoption as well. So they're using this TPS though, but it's very misleading because it doesn't represent usage of the chain or adoption at all, which it does with most other networks. So in fact, most of the network traffic is controlled traffic. So we run a Solana node and validator. So as we can see, but you can also go to SolScan and see all of this data. When validators vote on the leaders' work, they use the same highway as the network's transaction. And Anatoly says this, like, yes, we do this because we created the best system. We use it. We want to use it for our validators too, of course. Like, why should we use another system for that? Which kind of makes sense in a way when you hear him say that. But if you like really looking deeper, so what they have is they separate this metric into non-vote transactions and vote transactions. Okay, so non-vote transactions, that's real transactions on the networks, that's usage. And vote transactions, that's just validators voting on each other to like, are you a good boy? Are you a good boy? Are you a good boy? So in their network, the non-vote transactions, the real transactions, are pretty low in relation to just validators voting on each other. So if you look at like the distribution of real transactions on the chain versus non-transactions, so that they're counting like everything as total TPS for the network. That's the point. But 95% of the traffic, it's just vote. And 5% is real transactions. So out of like 4,000 transactions, only 200 are real transactions, which is kind of nuts, but it's that's how it is. And out of those real transactions, 70% of them also fail, but they count them too. So 95% of transactions are just messages between nodes that are exchanging blocks and resolving forks. So, and the thing with this is that Solana voting, it takes a lot of bandwidth from normal transactions. So the other thing with that is that when the number of nodes increase, as we can see here with time, okay, the votes also increase too, of course. If we compare these two charts, we can see that they're pretty much they're pretty much having the same curve, despite like even though like the vote transactions increase with time, even though the non-vote transactions, the real transactions, even like decrease with time or are the same. So the question is like, this is like contradictory to scaling and decentralization. Like really, like you want more nodes for the network, but if you increase the number of nodes, you're adding a lot more votes for the network to handle. So we don't do any forking. So since we don't have forking, there's no extra overhead of any processing, because we do like this avalanche style of probabilistic consensus. So the concept of neighborhood, which I should talk about in another stream. So with this gossip protocol, and that's why it's called avalanche, because it's like a snowball that's escalating, which is super interesting, because it basically says that already after there are a few confirmations, you can be sure that what you look for is 99.99% correct. So if you look at 100% consensus, it's slow. But if you reduce it to 99.99%, it's much easier. But in that case, you don't also have as much noise as Solana, because they use hard consensus. But the thing is, they report this 4,000 transactions per second, and it's you can call it like quadratic difficulty, and only 5% of them are real transactions. And out of those 5%, as we can see here, successful transactions, 25%. So like 74% of them, when we looked at this, are failing. And so why are these failing? And we think that because the transaction cost is super low, people write bots. This is Jack's theory. He should really talk about this, but this is what he thinks. So people are writing bots. They try to front run. So the validators are failing them because they probably come through, some of them. But the Solana network will reject because they don't match, right? But it's so cheap, so they're going to do it. And they're not using this probabilistic consensus, where the most common right is the right one. So Firedancer, which gets a lot of hype right now, which is the Solana client in C language, which they think will make everything faster. Like speed itself is awesome, and it looks great for marketing, but the speed of input of transaction, it doesn't solve anything. And we think we can just be faster using open source tech, because their issue is not the speed of the client, but the sequential processing of slots, which leads to this constant forks for the validators to handle. I mean, this, guys, I'm telling you this, it's not FUD in any way. We just try to understand the system. But and please explain if we got anything wrong here, because if this is true, it's not really, it's kind of misleading. But on the bright side, it looks great for marketing. They're really good at making glossy charts. You have to say that. But when you see, like, if you're going to make a chart comparing transactions per second like this, you really got to question, like, what is it really we're looking at? Like, there's a lot of this transactions that is like, the question is, like, if you increase more validators, what happens with time? Like when the network grows, when it really gets loaded with a lot of traffic, like will it actually work with time? But I don't know. The response from Vitalik from Anatoly, when he gets confronted, or what to say with this, it's like he says it's not that Solana counts votes as transactions, it's that votes are transactions, but they are counting them as transactions. That's the thing. He also says, like, every time hardware improves with Moore's law, there's more capacity for applications and for consensus, because it's the same thing. More cores, more capacity, more validators, more censorship resistance. But not if it's badly designed. There's like n times n minus 1 divided by 2 transaction votes for every new node. So it's also this, like Serum, one app does 20 million transactions per day, which is bigger than all the other chains combined. Yes, but that doesn't have anything to do with votes. Having to vote with votes is counted as transactions. TPS load is not a measure of users' adoption. It's a measure of load and an indicator of cost. Transactions are cheap, so there's build use cases that use them. But yeah, but it can be like a measure of usage adoption if you count it right. So we want to have a system where the system isn't taxed for new validators to onboard. That's the thing. That's Avalanche cracked that one, because the more they add validators, it doesn't increase the number of the tax on the network, because they're using this gossip style, which we want to simplify. Another thing is like the validator requirements, which is I mean, like, listen, Solana does a lot of cool stuff too. We're just pointing out like where the things are we would do differently, because the validator requirements is something that they've been criticized for a lot. It costs a lot with equipment, right? The pushback is that an ETH validator has to stake 32 ETH, which that's their pushback, which costs a lot more, which is also true. But it remains to see how low we can make the requirements to become a validator. And you can't ballpark that now, because it's like asking for the rental price of a Volvo on the secondhand market, while we're still in the factory and designing the engine, really. But what we can do right now is to break down all the pieces apart and design the system more based on first principles. So we think it should be able to reduce a lot based on the extra overhead we theoretically shouldn't have to do. Solana doesn't have a minimum stake. That's the last thing I want to point out. But validators have to pay for this voting with each of their transactions. But we think that it's hard to attack the network if it's proof of work, because we actually require you to compete with the network to produce blocks. Solana doesn't require competing. So in conclusion, like the thing we ask ourselves in this system is if we can make it this instead, like a system where we don't have time delays, no forks, no duplicate blocks, and a much faster finality. So can we eliminate forks and all of this stuff? Less network chatter. They're having sequential block production versus parallel block proposing with probabilistic finality. Is the other thing. Can we have a better token distribution? Yes, we already do. Thanks for Christopher, my Norwegian new friend who created this, who I love very much, even though it's Norwegian. Swedes and Norwegians have this thing. It's like a friendly thing. They think we're super stupid. We think they're stupid. Probably both true. Anyway, but the token distribution is just like horrible with Solana, as with many others. So we think we can be faster, have a better token distribution. We already do. And can we be faster, which is their main USP? I mean, we think so. So yeah, we want to look more also at Avalanche, because they did a lot of cool stuff. Kevin Seknicki at Ivy Labs, super smart guy. Yeah, guys. Okay. Shit, it took 3 hours. I can't believe there's still some people here. Let me know if there's some questions. I will just do a quick recap, and then I will see if there's some questions at all. So let's just go through. There was a lot of information, but you've seen me quiet for a few days. This is what happens. I'm sorry, not sorry. So yeah, we went. You know what to say now. Let's go this, which was just pure insanity, like in the beginning when you heard it. But maybe it makes sense now. It's a monolithic or semi-modular asynchronous delegated proof of consensus and parallel block production blockchain with probabilistic consensus and memory hard cryptographic hashing algorithm to mine Xenium with self-custodial hashing and social consensus for being hashed. Do I have your number or not? That's what you tell the girl. We walked through like the blockchain structures and to think about like the modularity, the level of modularity we want, and we're still researching, guys. We're doing a lot of research. We don't want to rush anything. I don't give a fuck if there's a bull market happening tomorrow. We need to get this right. It's the most important thing of everything. We need to continue experimenting and doing shit. You know now how simple it is to mine XenBLOCKs with proof of work mining and the things you need to think about. And really, the proof of work is really just rent or buy. Just rent it initially, get some heat up, and make sure you can deploy the script. And then once you get that up, use the performance bot. There's also another one in the community who's making this in a browser version. I haven't had time to look at that, but that's also very cool. And Argon 2, our baby, the engine of the vehicle, of the spacecraft. Self-custodial hashing, self-custody for the win, and some underlying protocols. TCP quick we use to transfer data. It's very fast. And then lib peer-to-peer as the data availability layer. But we also use WebSockets between the coordinators, so they can have like 2 open channels open at the same, like a channel open continuously, so they can stream data very fast. Because as you know, like the coordinator, the more data the coordinator has shared with them, the faster we can have consensus, and the faster we can be sure about the confirmations later on finality. We talked about some tests we've done, and like just the fact that nodes are talking to each other, they can like talk directly to each other, right? That's the whole point with a peer-to-peer network, that you have peers who are communicating with each other without some sort of central thing. Yada yada yada. It's pretty cool. We got it up and running there already. What else? Yeah, just how it all fits together. Like when you combine all of these models, we have a peer-to-peer network and a process from mining to reaching consensus in a peer-to-peer network. Some with transactional properties. We should dig more into this, but this is sort of just a starting way of thinking and compartmentalizing it. The block production process, parallel block production, active coordinator rotation, and participation. This is like V0.1, but most of the parts are there, I'd say. And we looked at a little bit at Solana, but other than this, they're great. Yeah. So how did you learn about all of this? Self-study or formal education? A lot of this, what I walk through now, is just like I've learned in, like, you compartmentalize things you've learned, like things fall into place. But the last 3 weeks, it's really been like insane for me personally, because I've just been not trying to have anyone talk to me or talk to anyone, just listening, learning a lot from Jack, because he knows a lot about this, and then taking parts of this and then just doing a bunch of research, because it's really about, like, you know, you have sort of surface level on a bunch of this stuff, but then to really understand things, you really, like, I never had a reason to look up like how lib peer-to-peer works, but now I did. So it sounds like I'm very knowledgeable about this, but it's really like just compartmentalizing all of this, and it's really Jack, guys, who's done, like, figured out all of this, and Nick and we have awesome guys with Nick and Leo. They're like super smart. So it's really for you just to like think about, like, the most important thing is just to have an overview and understand a little bit, and then step by step trying to learn all these different things, how it relates together. Has there been any utilization of zero knowledge proofs with X1? No, not too much. This is more like on a like foundational level still. So the need for zero knowledge is like, then we have to figure out, okay, what, because we're still like modeling like very broad scopes, the painting of all the things that needs to be there, and then you sort of see like where is the need for zero knowledge true to happen. I don't know what you're referring to. By having these indications, people are probably going to scurry and copy us. Yeah, and they can, and they if they want, they are welcome to do so. The thing is, that's our philosophy. We believe like really in transparency and open source and sharing education, because if we share this, we have done all the way from the beginning with the community. If we share all the information like ASAP, like Jack does this, and I do it all the time as well. We have an idea and then we communicate it. What do you think of this? And this, like the other extreme case of going about building is to invent stuff, creating intellectual property on it and patents, and like, this is mine, and then sue anyone who's tried to steal that. But the philosophy of open source is more or less like, for transparency's sake, share as much information about it as possible, because our strength is that we have an educated community. That's really the strength that we need. And the pace of what we're building with is so fast, so then we can be competitive in that way instead. Because usually if you have a corporation, like the amount of time they spend with lawyers and with trying to protect their information, etc., we spend that time on creating new tokens instead. I'm kidding. On like full on development building. Can't tell because you've been yeah, but yeah, I think it's like important that like you guys see this. I mean, that's the whole point with education, is that you have. I'm not trying to reach the masses. Like, that's my main goal of education has always been to like get, if we can get 100 people to watch it, get educated about it, then that can create a propagation chain to the rest, and that's how we create a strong community. So that's sort of what I've been trying to do all along. Like, take whatever's in Jack's 96 core head and put it on a paper, because he's running so fast. Like, this guy is seriously smart. But when also he speaks, it's like understandable. Like, I don't even understand sometimes, because he's so channeled in to what he says. So I really got to think about what he says for some time and then compartmentalize it. I'm more like, it takes some my processing time in my RPC node head is a lot slower than Jack, to say that. But it's cool, because then I think about stuff, how to boil it down into something more understandable. Anyway, can dApps and DAOs be created before a chain is created? Yeah, but we don't really know. Like, I mean, probably like sooner rather than later, you can start thinking about those stuff. But there's still like a lot of iterations in the data availability layer and consensus layer that needs to happen. So things change quite a lot. But we think that like NFTs as a use case is pretty interesting, due to the fact that if we can be very fast, then that is interesting. I mean, if you look at Solana, that's sort of like they built up a huge ecosystem for NFTs. So that's something that's interesting to follow up on. Yeah, exactly. No one questions allowed. Thank you very much, Jax. Oh, okay. X1. This is from OKX. Rebrand happened 2 days ago. That's interesting. Yeah, that was a psyop. It's another thing. Zentronaut. OKX just became the marketing wing for the real X1 community with blockchain. Same community can play this to our advantage. There's something to be played here, guys. Believe me, Jack is he's using 30% of his 96 cores to see what to do with this. Let's see. Thank you very much. Yeah, exactly. Yeah, I tried to Eli 5 everything. That's the thing. Anyway, guys, thanks for sticking through so long. I hope it was valuable. I want your input on this, guys. Like, what makes sense to you? What doesn't make sense? Like, the whole concept of proof of work mining. Share your thoughts. It's a lot of questions of when, but we're still in mode like of building. Okay, we're just building right now. We're just seeing the technology, the capabilities of what can be done, because there's no reason to rush anything to market if it needs to be quality to the bone. Because when you're creating a chain, it's like that's it, and then you can have updates, and you need some kind of governance to solve that. Like, do you have on-chain, off-chain governance and all of that? That's a whole other thing. We're sort of more inclined to run everything like a Linux thing, like release the tech, it's immutable, it's out there, and then but for that to happen, you really need to make as much as possible packaged into the foundations as possible, and it needs to be good. Yeah, quality is definitely number one, and having fun too. Like, we're learning a lot. But let me know what you think about if there's other like technologies that are interesting, tests, this whole model of delegated proof of consensus, etc., etc. So yeah. Why are you asking this? What doubts do you have? I don't know what you're referring to. No, okay, yeah. Why I'm asking this? No, I wanna. We always want feedback. What you guys think about it? There's not so much doubts. I think like things are pretty. It's pretty cool. It's pretty cool. But at the same time, we're building like an engine. Like, I'm just astounded by how fast Jack has put all of this like together. You know, and I've been happily following along and giving my inputs, but it's kind of cool how fast this project has evolved. So there's no real doubts in my mind. I'm more excited about it. Like, is this whole, or have we missed something, or anything? Like, is there, because this way of model, there's something here. Let's just say that. Anyway, guys, thanks for tuning in to Education. You fucking hash heads. Have a good day. I love you all as always. And yeah, let's fucking hash. Let's fucking hash. See you guys.